Jupiter, the most massive planet in the solar system, is located outside the asteroid belt and ranks sixth in the distance from the Sun. It is among the most luminous entities in the nocturnal sky. Only the Moon, Venus, and occasionally Mars surpass its brilliance. Ancient scientists designated Jupiter after the Roman deity of gods and the skies, unaware of its actual size. Yet, the nomenclature is fitting, as Jupiter surpasses the aggregate dimensions of all other planets. The planet completes an orbit around the Sun in approximately 12 Earth years and rotates once every 10 hours, more than twice Earth's rotational speed. A little telescope can disclose its vibrant cloud bands. Jupiter possesses a slender ring system and over 60 recognized moons, including one larger than Mercury and 3 exceeding the size of Earth's moon. Certain astronomers hypothesize that Jupiter's moon Europa may conceal a warm water ocean and potentially some form of life beneath its frozen surface. Jupiter possesses an internal heat source, emitting more energy than it absorbs from the Sun. The pressure within its deep interior is sufficiently elevated for hydrogen to exist in a fluid metallic state. This colossal planet possesses the most powerful magnetic field of any planet, exhibiting a substantial magnetosphere that, when observed from Earth, exceeds the Moon's apparent diameter. Jupiter's system emits intense bursts of radio noise, sometimes radiating more energy than the Sun at specific frequencies. Despite its several superlatives, Jupiter is predominantly composed of hydrogen and helium, with an average density that scarcely exceeds that of water. Understanding of the Jovian system significantly advanced following the mid-1970s due to the investigations conducted by 3 spacecraft missions: Pioneers 10 and 11 in 1973-74, Voyagers 1 and 2 in 1979, and the Galileo orbiter and probe, which reached Jupiter in December 1995. The Pioneer spacecraft acted as precursors for the Voyagers, demonstrating that Jupiter's radiation levels were manageable and delineating the primary features of the planet and its surroundings. The augmented quantity and complexity of the Voyager instruments produced abundant, fresh data. The analysis was still in progress when the Galileo mission began. Prior missions were exclusively flybys. However, Galileo sent a probe into Jupiter's atmosphere and then entered orbit around the planet for comprehensive studies of the entire system over several years. The Cassini spacecraft's 2000 flyby of Saturn and the New Horizons spacecraft's 2007 flyby of Jupiter offered an additional perspective on the Jovian system. Route to Pluto. In 1994, observations of Comet Shoemaker-Levy 9's broken nucleus colliding with Jupiter's atmosphere provided insights into its composition and structure. Jupiter possesses an equatorial diameter of approximately 143,000 km, 900 miles, and revolves around the Sun at an average distance of 778 million km, 483 million miles. Noteworthy are the planet's low mean density, in contrast to Earth's, along with its considerable size, mass, and brief rotation period. The low density and substantial mass suggests that Jupiter's composition and structure significantly differ from those of Earth and the other terrestrial planets, a conclusion corroborated by comprehensive studies of the giant planet's atmosphere and innards. We have established 3 rotation intervals within a few minutes of each other. The 2 intervals designated System 1 total 9 hours, 50 minutes, and 30 seconds. The average figures for System 1, 9 hours, 55 minutes, 41 seconds, and System 2, 9 hours, 55 minutes, 41 seconds, denote the rotational velocity at the equator and elevated latitudes, respectively, as determined by characteristics detected in the planet's visible cloud formations. Jupiter lacks a solid surface. The shift from the gaseous atmosphere to the liquid interior transpires gradually at significant depths. The variance in rotation time at various latitudes does not indicate that the planet rotates at either of these average velocities. The actual rotation period of Jupiter is System 3, which is 9 hours, 55 minutes, and 29 seconds. The rotation period of Jupiter's magnetic field was initially inferred from terrestrial radio data and then validated through direct spacecraft measurements. This duration, consistent during 30 years of observation, pertains to the planet's substantial interior, where the magnetic field is produced. The atmosphere. A small telescope may reveal considerable details about Jupiter. Various clouds are arranged vertically and horizontally in the segment of the planet's atmosphere observable from Earth. Alterations in these cloud systems may transpire within a few hours. Nonetheless, a fundamental pattern of latitudinal currents has exhibited stability over decades. The planet's appearance is conventionally characterized by a standardized name for its alternating dark bands, belts, and light bands, known as zones. Nonetheless, the fundamental currents appear to have higher durability than this pattern. The close-up images of Jupiter sent to Earth by the Voyager probe displayed diverse cloud formations, including numerous elliptical characteristics akin to cyclonic and anticyclonic storm systems found on Earth. All these systems are dynamic, manifesting and vanishing over varying temporal scales and geographic locations. The pastel hues of the cloud layers exhibit variation, ranging from the tawny yellow that predominates the primary layer through browns and blue-grays to the renowned salmon-colored Great Red Spot, Jupiter's largest, most noticeable, and longest-lasting feature. Chemical variations in cloud composition, which astronomers hypothesize to induce color differences, clearly accompany the vertical and horizontal stratification of cloud systems. Jovian meteorology can be compared to the worldwide circulation of Earth's atmosphere. On Earth, extensive spiral cloud formations frequently extend across numerous degrees of latitude and are linked to the dynamics around high and low pressure areas. The characteristics of the Great Red Spot. Even with comprehensive observations from the Voyager and Galileo spacecraft, the authentic characteristics of Jupiter's distinctive Great Red Spot remained elusive at the commencement of the 21st century. The Great Red Spot has persisted for at least 300 years, coinciding with comprehensive studies of Jupiter, a planet whose cloud patterns can change within days. Evidence indicates that the spot is gradually diminishing. Nevertheless, an extended series of observations is required to validate this assertion. The dimensions are approximately 20,000 by 12,000 kilometers, 12,400 by 7,500 miles, large enough to encompass Earth and Mars. The substantial dimensions are likely responsible for the feature's durability and unique coloration. The rotation period of the Great Red Spot does not correspond with any of Jupiter's 3 rotation periods. We have yet to effectively correlate its variability with other Jovian phenomena. Voyager observations indicated that the substance within the area rotates counterclockwise every 7 days, correlating with super hurricane force winds of 400 kilometers, 250 miles per hour at the edges. The Voyager photos documented several interactions between the Great Red Spot and significantly smaller disturbances across the current at the same latitude. The location's interior is notably serene, with no definitive indication of the anticipated upwelling or divergence of the material from deeper strata. The Great Red Spot is a massive anticyclone, a vortex or eddy with a diameter likely accompanied by significant depth, enabling it to extend well below and over the primary cloud layers. Reduced temperatures and less gas absorption above the Great Red Spot indicate its elevation above the primary cloud layer relative to adjacent areas. Observations of its inferior expansion are currently in progress. These cloud systems exhibit far less zonal confinement than Jupiter ones, and migrate according to latitude and longitude. The diverse characteristics of the planet's surface frequently influence the local weather on Earth. Latitudinal currents prevail in Jupiter's large-scale circulation due to the planet's absence of a solid surface and topographical characteristics. The absence of a stable surface with defined boundaries and areas exhibiting varying heat capacities renders the continuity of these currents and their corresponding cloud formations particularly noteworthy. The Great Red Spot, for instance, shifts in longitude relative to all three of the planet's rotational systems, yet it remains stationary in latitude. Comparable behavior is exhibited by the white ovals located at a latitude somewhat south of the Great Red Spot, which are distinctive to the planet. The dark brown clouds, clearly openings in the tawny cloud layer, are predominantly located about 18 degrees N latitude. Thermal emission is detected most intensely in the equatorial section of the planet, particularly from the blue-grey or purple parts. Composition of clouds. The planet's atmosphere generates the clouds observed through Earth-based observatories and recorded in images at various altitudes. Aside from the apex of the Great Red Spot, the white clouds represent the highest altitude, exhibiting cloud top temperatures of approximately 120 kelvins, K, 240 degrees, 150 degrees. These white clouds are frozen ammonia crystals, equivalent to the water ice cirrus clouds in Earth's atmosphere. The tawny clouds, extensively spread worldwide, exist at lower altitudes. They appear to originate at temperatures approximately 200 K, 100 degrees, 70 degrees, indicating they are predominantly composed of condensed ammonium hydrosulfide. Their coloration may result from other ammonia-sulfur compounds, such as ammonium polysulfides. Given the relative abundance of sulfur in the cosmos, and the lack of hydrogen sulfide in Jupiter's atmosphere above the clouds, we propose sulfur compounds as the probable coloring agents. Helium and hydrogen constitute the predominant elements of Jupiter's makeup. We anticipate that the plentiful chemically active elements will react with hydrogen under equilibrium conditions, enabling all existing elements to interact at an average temperature within the observable region of the Jovian atmosphere. Consequently, we inferred the existence of methane, ammonia, water, and hydrogen sulfide. Spectroscopic investigations from Earth have detected all these chemicals, with the exception of hydrogen sulfide. The apparent absence of hydrogen sulfide can be comprehended if it reacts with ammonia to create the hypothesized ammonium hydrosulfide clouds. The Galileo probe identified hydrogen sulfide at reduced concentrations in the atmosphere. The lack of measurable hydrogen sulfide above the clouds indicates that local lightning discharges, rather than solar UV radiation, likely initiate the chemical processes that produce colorful sulfur compounds, assuming they exist. The causes of Jupiter's hues remain unresolved. However, researchers have proposed various plausible possibilities. Sulfur compounds have been suggested to account for the dark brown hue of the ammonia clouds observed at lower altitudes, when the recorded temperature is 260 K, 8 degrees, 213 degrees. We observe these clouds through openings in the generally pervasive tawny clouds. Images of Jupiter, derived from its thermal radiation at a wavelength of 5 micrometers, 0.0002 inches, exhibit brightness, indicating their elevated temperatures. The coloration of the Great Red Spot has been ascribed to the existence of intricate organic molecules, red phosphorus, or an alternative sulfur chemical. Laboratory investigations corroborate these concepts. Nonetheless, counter-arguments exist for each instance. Researchers have recorded temperatures reaching 300 K, 80 degrees, 27 degrees, adjacent to the apex of white plume clouds at the planet's equator, where darker areas are also present. Notwithstanding their blue-grey hue, these designated hot areas exhibit a reddish tint. These places seem devoid of clouds, facilitating visibility into substantial depths and measuring elevated temperatures. The Rayleigh scattering of sunlight imparts a blue hue, then obscured by a thin layer of reddish substance. The occurrence of these so-called hot patches exclusively around the equator, the circular dark brown clouds only at latitude 18° N, and the most pronounced red coloration on the globe confined to the Great Red Spot, suggest a perplexing localization of cloud chemistry within such a dynamically active atmosphere. At greater depths in the atmosphere, astronomers anticipate the presence of water ice clouds and clouds composed of water droplets, which consist of dilute solutions of ammonium hydroxide. However, when the Galileo spacecraft's probe penetrated Jupiter's atmosphere on December 7, 1995, it did not detect the anticipated water clouds, despite enduring pressure of 22 bars, approximately 22 times the sea level pressure on Earth. Where the temperature exceeded 400 K, 260 degrees Fahrenheit, 130 degrees Celsius, the probe could not identify the highest ammonia and ammonium hydrosulfide strata within the clouds. Unfortunately for Jovian cloud physics research, the probe's atmospheric entrance transpired above a cloudless hot region, possibly attributable to a significant meteorological event, akin to the downdrafts seen in certain terrestrial storms. Atmospheric attributes. Before the deployment of the Galileo probe, astronomers depended on spectral studies of the planet to ascertain the composition, temperature, and pressure of its atmosphere. In the absorption spectroscopy approach, the dispersive component in a spectrograph separates light or thermal radiation from the planet into distinct wavelengths, colors as observed in a rainbow. The resulting spectrum exhibits distinct intervals, or lines, corresponding to the energy absorbed by the constituents of the planet's atmosphere. Astronomers can ascertain the gases in Jupiter's atmosphere by measuring the precise absorption wavelengths and contrasting the findings with laboratory spectra of gases. In the 1930s, scientists inferred the existence of methane and ammonia in Jupiter's atmosphere, and they identified hydrogen for the first time in 1960. Although molecular hydrogen is 500 times more common than methane, it displays considerably weaker absorption lines due to its minimal interaction with electromagnetic waves. Subsequent research resulted in an expanding catalogue of additional elements, notably identifying the arsenic compound arsine in 1990. If chemical equilibrium were strictly maintained in Jupiter's atmosphere, the observed abundance of compounds like carbon monoxide or phosphine would be unexpected. The presence of acetylene, ethane, and other hydrocarbons identified in the stratosphere contradicts predictions. Clearly, energy sources exist beyond the molecular kinetic energy associated with local temperatures. Solar ultraviolet radiation facilitates the decomposition of methane, leading to subsequent processes that generate acetylene and ethane. The Voyager and Galileo spacecraft detected lightning discharges in the atmospheric convective zone, contributing to these phenomena. A reaction between methane and water vapor generates carbon monoxide at around 1200 K, 1700 degrees 930 degrees Celsius. The vertical mixing must be robust to detect this gas from beyond the atmosphere. A portion of carbon monoxide, carbon dioxide, and water in the atmosphere originates from ice particles impacting the planet from space. Galileo's probe was equipped with a mass spectrometer that identified the constituent atoms and molecules in the atmosphere by initially charging them and dispersing them using a magnetic field based on their masses. This technology possessed the benefit of measuring noble gases such as helium and neon, which do not interact with visible and infrared light. While the probe plummeted through the atmosphere on its parachute, its spectrometer analyzed fluctuations in abundance with altitude. This experiment successfully identified the previously undetected hydrogen sulfide, demonstrating its presence at a lower altitude in the atmosphere than anticipated. Clearly, the previously indicated downdraft diminished the concentration of this cloud-forming gas in the top region of the hot area, as well as ammonia and water vapor. Measuring oxygen proved unfeasible, as this element is encapsulated in water, and the probe did not penetrate sufficiently into the hotspot to access the atmospheric zone, where this condensable vapor is homogeneously distributed. We can juxtapose the elemental abundances in Jupiter's atmosphere with the solar composition. If the planet formed similarly to the Sun through basic condensation from the original solar nebula that is thought to have originated the solar system, their elemental abundances should be comparable. The Galileo probe yielded an unexpected finding. All globally mixed elements measurable in the Jovian atmosphere had the same threefold hydrogen enrichment compared to their Sun levels. This has significant implications for the planet's development. See origin of the Jovian system later in this chapter. Spectroscopy conducted from Earth indicates a significant variation in the concentrations of other elements, specifically phosphorus, germanium, and arsenic, which were not assessed by the probe. The concentrations of the gases resulting from these elemental abundances are contingent upon dynamic processes in Jupiter's atmosphere, namely chemical reactions and vertical mixing. The existence of deuterium on Jupiter signifies an additional divergence from solar values. This dense hydrogen isotope has vanished from the Sun due to nuclear events within its center. Since no such reactions transpire on Jupiter, the deuterium to hydrogen ratio should mirror that of the isotopes present in the interstellar gas and dust cloud that collapsed to create the solar system 4.6 billion years ago. The Big Bang, thought to have commenced the universe's expansion, generated deuterium. Thus, a more accurate measurement of Jupiter's deuterium-to-hydrogen ratio will facilitate the calibration of expansion models. Thermal and barometric conditions. Besides assessing atmospheric composition, the Galileo probe was equipped with equipment to measure temperature and pressure during its fall into the Jovian atmosphere. The probe recorded temperatures beyond the freezing point of water, 273 K, 30 consecutive, 0 degree Celsius, at pressures slightly above Earth's sea level pressure, about 1 bar. This phenomenon is mostly attributable to Jupiter's internal energy supply, but some warming may also result from the atmosphere's retention of infrared radiation, akin to Earth's greenhouse effect. The rise in temperature above the tropopause is referred to as an inversion, as temperature typically diminishes with altitude. At high elevations, gases and aerosol particles absorb solar radiation, resulting in the inversion. Ozone induces a comparable inversion in the Earth's atmosphere. Additional probable atmospheric components. Astronomers and various other unusual entities anticipate the presence of monosilane in the deep atmosphere. Additional out-of-equilibrium species are expected to exist in the elevated regions, accessible to future atmospheric missions. These species may originate from chemical reactions initiated by lightning or ultraviolet radiation from the Sun, or they could develop near the poles, where charged particles have been observed to facilitate the production of benzene. The synthesis of intricate organic molecules in Jupiter's atmosphere is important in investigating life's origins. The primordial chemical processes that contributed to the emergence of life on Earth may have transpired in ephemeral microenvironments akin to Jupiter's current chemical makeup, albeit devoid of substantial quantities of hydrogen and helium. Consequently, Jupiter may function as an extensive natural laboratory in which scientists continuously investigate the preliminary stages of life's origin. Assessing the complexity of prebiotic chemical reactions under such settings represents a compelling challenge for any space exploration initiative. On March 25, 1993, Eugene, Caroline Shoemaker, and David Levy discovered an unidentified comet near Jupiter in photos captured at Palomar Observatory in California. Its look was unusual. It featured at least a dozen cometary nuclei, arranged like luminous pearls on a thread. Over successive weeks, the nuclei dispersed increasingly, resulting in the visibility of 21 fragments. An examination of their shared orbit indicated that the original comet, orbiting the Sun, had skimmed Jupiter's atmosphere and nearly collided with it on July 8, 1992. During that period, the tidal gravitational forces exerted by the massive planet fragmented the nucleus into numerous parts, which were subsequently captured by Jupiter's gravity and sent into an extended 2-year orbit around the planet. Astronomers determined that the revised orbit would return the fragments to Jupiter in July 1994. The shards of Shoemaker-Levy 9 collided with Jupiter's atmosphere at a speed of 216,000 kilometers, 134,000 miles per hour, commencing on July 16, 1994. All of them slammed with the imperceptible side of Jupiter beyond its limb, as observed from Earth. The planet's 10-hour rotation rapidly exposed each impact location. Separated by an average of 7 to 8 hours, each component descended into the Jovian atmosphere, creating prominent scars situated near latitude 44° S. Astronomers designated the individual components with capital letters sequentially based on their arrival. Fragment G was likely the largest and heaviest, with an estimated diameter of 3 to 4 kilometers, 1.9 to 2.5 miles. It created a black, multi-ringed mark, twice the circumference of Earth. The collision released energy equivalent to several trillion tons of TNT, surpassing the yield of the global nuclear arsenal by hundreds of times. Each collision rapidly evolved into a vast bubble of heated gas that emitted a warm glow in infrared photos of Jupiter, as it spread over several days within the atmosphere. The extensive band of dark brown blemishes, presumed to be minute organic cometary particles, persisted in visibility for several weeks. The intense winds of Jupiter gradually diminished its prominence, forming a new, slender belt. Spectroscopic analyses indicated that the impacts generated or introduced various molecules, including water, hydrogen cyanide, and carbon monoxide, compounds present on Jupiter but in significantly lower proportions. The surplus carbon monoxide and hydrogen cyanide persisted in the upper atmosphere for several years following the incident. Besides its inherent significance, the collision of a comet with Jupiter prompted comprehensive investigations into the consequences of cometary impacts on Earth. A black patch resembling pieces of Comet Shoemaker-Levy 9 emerged near Jupiter's southern pole in 2009. The observation of a singular impact site prompted scientists to conclude that the hitting entity was a solitary body, a comet, or an asteroid, rather than a series of fragments. In 1955, Jupiter was identified as the inaugural planet to emit radiation at radio wavelengths. Researchers documented the radiation at a frequency of 22 megahertz, corresponding to a wavelength of 13.6 meters, 44.6 feet, or 1.36 decameters as noise bursts. Occasionally, the maximum intensities of these bursts rendered Jupiter the most luminous object in the sky at this wavelength, surpassed only by the Sun during its peak activity. The emissions of radio interference from 3 separate regions represented the initial proof of a Jovian magnetic field. Later measurements at shorter, decimeter, wavelengths indicated that Jupiter is additionally a source of continuous radio emissions. It has become standard to designate these two forms of emissions by their characteristic wavelengths: decameter radiation and decimeter radiation. The non-thermal component of the continuous decimeter radiation is attributable to synchrotron emission. This phenomenon is attributed to electrons traversing at exceedingly high velocities within Jupiter's magnetic field in a toroidal region surrounding the planet. This phenomenon closely resembles Earth's Van Allen belts. The Cassini orbiter identified the peak emission at 13,800 megahertz, the operational frequency of the spacecraft's radar instrument, from Earth at a distance of 2 planetary radii from the planet's core. The emission intensity and its polarization plane the plane where radio emission oscillations predominantly occur, fluctuate with the same periodicity. Both phenomena are elucidated if the axis of the planet's magnetic field is tilted approximately 10 degrees relative to the rotational axis. System 3 identifies the rotation period as the duration of these variations. Researchers have investigated intermittent radio emissions at decameter wavelengths from Earth, within the frequency range of 3.5 to 39.5 MHz. Unimpeded by Earth's ionosphere, which obstructs lower frequencies from penetrating the surface. The radio wave experiment aboard the Voyager spacecraft successfully detected emissions from Jupiter as low as 60 kHz, equating to a wavelength of 5 kilometers, 3 miles. The intensity of the radio signal and the frequency of noise storms exhibit a significant temporal correlation that facilitated the early identification of 3 sources, or emitting locations. The rotational period of System 3 was originally established based on the periodicity of these sources. The orbital position of Jupiter's moon, Io, significantly influences the decameter noise storms. According to one source, events are far more probable when Io is positioned 90 degrees from the alignment of Earth, Jupiter, and Io, termed superior geocentric conjunction, than in other configurations. In contrast to non-thermal decimetric radiation, the noise sources seem to be areas located in the line of sight to the planet's visible disk. The magnetic field lines, or flux tubes, associated with Io connect the emissions to a localized area, offering the most compelling explanation for how Io's orbital motion influences noise storms. Electrons spiraling around magnetic field lines may generate the observed radiation. The Voyager and Galileo spacecraft anticipate and detect interactions between these electrons and the Jovian ionosphere. Earth can detect the footprint of Io's flux tube on Jupiter's upper atmosphere as a luminous spot linked to Jupiter's polar auroras. The magnetic field and magnetosphere. The aforementioned non-thermal radio emissions are a natural consequence of trapped charged particles interacting with Jupiter's magnetic field and ionosphere. The Pioneer and Voyager spacecraft's direct examination of Jupiter's surroundings resulted in a highly precise characterization of the planet's magnetic field and magnetosphere through the analysis of these observations. The hydromagnetic dynamo in Jupiter's electrically conductive outer layers produces the planet's dipolar fundamental magnetic field. The magnetic moment is 19,000 times superior to Earth's, resulting in an equatorial field strength of 4.3 Gauss, in contrast to 0.3 Gauss at Earth's surface. The magnetic dipole axis is displaced by 1/10 of Jupiter's equatorial radius of 71,500 kilometers, 44,400 miles, from the planet's rotational axis, to which it is inclined by 10 deg. A terrestrial compass oriented towards Jupiter would indicate south, because the Jovian magnetic field is opposite Earth's current magnetic field. The magnetic field predominates the area surrounding Jupiter, forming an elongated teardrop shape. The rounded side of the teardrop orients towards the Sun, while the Jovian magnetic field deflects the solar wind, creating a bow shock approximately 3 million kilometers, 1.9 million miles, from the planet. Opposite the Sun, a vast magnetotail extends to the orbit of Saturn, almost 650 million kilometers, 404 million miles away, nearly equivalent to Jupiter's distance from the Sun. These dimensions render Jupiter's magnetosphere the largest enduring structure in the solar system, surpassing the Sun's diameter of 1.4 million kilometers, 870,000 miles. Io, the Moon, produces the most remarkable activity in this extensive area, and the preceding section examines its impact on decametric radiation. An electric current of roughly 5 million amperes traverses Jupiter and Io's magnetic flux tube. This satellite generates a toroidal cloud of ions, or plasma, encircling its orbit. The energy sustaining this vast magnetosphere originates from the planet's rotation, which must consequently be decelerating at an imperceptibly modest pace. Charged particles, such as electrons, are compelled to traverse the planet in alignment with the magnetic field lines, moving at a velocity corresponding to the planet's rotational cycle. Consequently, terrestrial radio astronomers could ascertain System 3's rotation period long before any spacecraft detected it. The entrapment of charged particles by the Jovian magnetic field causes the ions released by Io during its orbit to oscillate with the System 3 period of around 10 hours, rather than the 42.5 hours required for Io to complete one revolution around Jupiter. Consequently, Io's plasma wake precedes the Moon's orbit around Jupiter. The auroras, like charged particles confined within the Van Allen belts generating auroras on Earth, upon colliding with the upper atmosphere near the magnetic poles, they cause auroras on Jupiter. The Voyager and Galileo spacecraft cameras successfully captured images of ultraviolet auroral arcs on Jupiter's night side. The Hubble Space Telescope also obtained photographs of far ultraviolet auroras on the planet's day side. Furthermore, terrestrial investigations have detected infrared emissions from H+ ions at both poles and captured images of the corresponding polar auroras. Protons, hydrogen ions, H+, from the magnetosphere spiral into the planet's ionosphere along magnetic field lines, generating excited H+ ions upon colliding with the atmosphere predominantly composed of molecular hydrogen. The resultant emission generates auroras, detectable from Earth at wavelengths, when methane in Jupiter's atmosphere exhibits significant absorption bands, thereby diminishing the background from reflected sunlight. The correlation between ultraviolet and infrared auroras, the intricate interaction of Io's flux tube with Jupiter's ionosphere, and the potential impact of ions from Io's torus on the planet's atmosphere continue to be subjects of ongoing research. The interior. Jupiter's atmosphere represents but a minuscule portion of the planet, analogous to the skin of an apple in relation to its inside. We infer the composition of Jupiter's interior from the evidence, as direct observation of anything beneath the thin outer layer is not feasible. Astronomers can utilize the observable quantities of air temperature and pressure, mass, radius, form, rotational velocity, thermal equilibrium, and disturbances in satellite orbits and spacecraft trajectories. From them, we can ascertain the planet's ellipticity, or deviation from a perfect sphere, and its divergence from an ellipsoidal form. Theoretical models for the internal distribution of materials can also forecast these subsequent quantities. Subsequently, we can evaluate these models by juxtaposing them with the observations. The primary challenge in developing a model that accurately represents the internal conditions of Jupiter is the need for comprehensive laboratory data regarding the characteristics of hydrogen and helium under the extreme pressures and temperatures found near the planet's core. Estimates suggest the center temperature is roughly 25,000 K, 44,500 degrees, 24,700 lodigellus, signifying an internal heat source that allows Jupiter to emit nearly double the energy it absorbs from the Sun. The core pressure ranges from 50 to 100 million atmospheres, equivalent to around 50 to 100 megabars. We anticipate hydrogen to manifest in a metallic state under such immense pressures. Notwithstanding the challenges in determining the properties of matter under these high conditions, the accuracy of the models has consistently enhanced. One of these investigations' most significant early discoveries was that Jupiter cannot consist only of hydrogen, which would necessitate a considerably bigger size to correspond with its mass. Conversely, hydrogen must be the predominant element, comprising no less than 70% of the planet's mass, irrespective of its state, gas, liquid, or solid. The Galileo probe detected a helium mass fraction of 24% in Jupiter's upper atmosphere, in contrast to the 28% anticipated if the atmosphere mirrored the composition of the primordial solar nebula. Astronomers have determined that certain helium dissolved in the fluid hydrogen within the planet's interior precipitated from solution and descended toward the planet's core, resulting in a depletion of this gas in the atmosphere. This is because the planet collectively ought to possess that primordial composition. Clearly, the globe has assimilated a substantial quantity of neon. This precipitation persists while the globe continues to cool. Contemporary models concur that the transition from molecular to metallic hydrogen occurs roughly 1/4 of the distance to Jupiter's core. This transition is not between a liquid and a solid, but between two fluids with differing electrical characteristics. The metallic state liberates electrons from their nuclei, endowing hydrogen with metallic conductivity. No solid surface is present in any of these models. However, the majority, though not all, include a dense core with a radius ranging from 0.03 to 0.1 times, that of Jupiter 0.33 to 1.1 times the radius of Earth. We must fully ascertain the origin of internal heat. The preferred theory posits a combination of the gradual release of primordial heat from the planet's formation and the release of thermal energy from the precipitation of helium droplets in the planet's deep interior, similar to phenomena observed on Saturn. The diminished helium concentration in Jupiter's atmosphere, compared to the Sun's, corroborates this conclusion. The initial step is the cooling phase of the original collapse, which transformed potential energy into thermal energy when the planet gathered its share of solar nebula gas. See origin of the Jovian system. The initial celestial bodies in the solar system identified using a telescope by Galileo in 1610 were the 4 most luminous moons of Jupiter, now referred to as the Galilean satellites. In 1892, Edward Emerson Barnard visually discovered the 5th known Jovian moon, Amalthea. Photographs, or computerized images captured by Earth-based telescopes or the cameras on the Voyager spacecraft, have identified all other known satellites. In 1979, Voyager photos unveiled Jupiter's multifaceted ring system. Appendix A, titled Moons of Jupiter, is a table that summarizes data regarding the known Jovian satellites. The trajectories of the 8 inner moons exhibit minimal eccentricities and inclinations. That is, their orbits are predominantly circular and aligned with the planet's equatorial plane. These moons are termed regular. The orbits of the numerous moons located beyond Callisto exhibit significantly greater inclinations and eccentricities, categorizing them as irregular. The 2 innermost moons, Metis and Adrastea, are closely linked to Jupiter's ring system, serving as sources of fine particles and acting as gravitational shepherds. Amalthea and Thebe also contribute to the ring system by generating delicate gossamer rings, positioned slightly farther from the planet. Other unknown minor moons may exist in proximity to Jupiter. Further distant irregular moons may exist beyond those now identified. The Galilean moons. Galileo suggested naming the 4 Jovian moons he discovered in 1610 the Medicean stars, in tribute to his patron, Cosimo II de' Medici. Nevertheless, they subsequently became known as the Galilean satellites in recognition of their discoverer. Galileo considered their existence vital evidence supporting the Copernican heliocentric paradigm, wherein the planets revolve around the Sun. Sun-hour orbits around Jupiter were a blatant contravention of the Ptolemaic system, which mandated that all heavenly bodies revolve around Earth. Greek mythology intimately links the satellites Io, Europa, Ganymede, and Callisto, arranged in ascending order of their distance from the planet. Simon Marius, a German astronomer and contemporary rival of Galileo, undoubtedly discovered the satellites independently and designated their names. The selection of Io's name demonstrated notable relevance. Io, the wanderer, Greek, ion, going, exerts an indirect effect on Jupiter's ionosphere. Observations from Earth had ascertained the approximate sizes and spectroscopic properties of the Galilean moons, but the Voyager missions unequivocally confirmed these four entities as distinct worlds. The Galileo mission yielded an abundance of supplementary data. Before Voyager, we were aware that Callisto and Ganymede are comparable in size to or exceed the dimensions of Mercury, that their surfaces, along with Europa, are enveloped in water ice, that a toroidal structure of atoms and ions, including sodium, potassium, and sulfur, encircles Io's orbit, and that the average densities of the two inner Galilean moons are markedly greater than those of the two outer moons. The density gradient from Io to Callisto resembles that of the solar system and originates from the same source. The density values suggest that Io and Europa have a stony composition similar to the Moon, whereas Ganymede and Callisto likely contain a far less dense material, presumably water ice. Callisto. Impact craters predominate the frigid surface of this satellite, precluding the existence of flat plains akin to the dark maria observed on the Moon. In other words, there are no regions on Callisto where the emergence of material from beneath the surface, resulting from subsequent internal activity, has erased any evidence of early bombardment. This record was created by the collision of debris, comet nuclei and asteroidal material, mostly during the initial 500 million years following the solar system's birth, analogous to the production of craters on the Moon. The unchanged surface appearance aligns with the lack of a differentiated inside. In contrast to the other three Galilean moons, Callisto did not experience tidally driven global heating and subsequent melting. Deposits of fine, black material, akin to a blend of clay minerals, obscure craters smaller than 10 kilometers to 6 miles, as demonstrated by the Galileo spacecraft. In addition to the prevalent water ice, the surface comprises solid carbon dioxide, while a highly tenuous atmosphere of carbon dioxide gradually dissipates into space. Additional trace surface components include solar ultraviolet energy induces photochemical processes in ice that generate hydrogen peroxide. Sulfur and its components are presumably derived from Io. Cometary collisions may have introduced organic molecules. Jupiter's magnetic field generates a faint magnetic field on Callisto, suggesting the potential existence of a subsurface liquid water layer beneath its icy cover. Ganymede. In contrast to Callisto, Ganymede, another frozen satellite, exhibits well-defined dark and light terrain regions. This difference resembles the Moon's surface. However, the inquiry into which terrain originated, first, dark or light, is fundamentally reversed. Unlike the Moon, the darker areas on Ganymede are more ancient, exhibiting the highest density of craters. The illuminated areas indicate a more recent age. Ray systems generally encircle the intricate arrangement of parallel and crossing ridges and grooves, accompanied by exceptionally luminous impact craters. Conclusive evidence of internal differentiation accompanies active crustal movement and resurfacing. In contrast to Callisto, Ganymede possesses an iron-rich core and a permanent magnetic field sufficiently robust to generate its magnetosphere and auroras. The trace constituents detected on Ganymede's icy surface comprise a lesser quantity of the clay-like dust present on Callisto, alongside identical quantities of solid carbon dioxide, hydrogen peroxide, and sulfur compounds, in addition to indications of molecular oxygen and ozone encapsulated in the ice. Europa. Although the infrared spectra of Ganymede and Callisto indicate ice coverage, Europa's surface is markedly distinct. Europa possesses a limited number of impact craters, with the density per unit area akin to Earth's continental regions, suggesting that its surface is very young. Certain experts believe the surface is sufficiently new that considerable resurfacing continues on the satellite. This resurfacing clearly involves the egress of water from the interior, forming an immediately frozen ocean. Models of the differentiated interior suggest the presence of an iron-rich core, surrounded by a silicate mantle, and capped by an ice crust roughly 150 kilometers, 90 miles, thick. This moon has both induced and intrinsic magnetic fields. Researchers have identified salt deposits in somewhat mottled areas on the lunar surface, suggesting the evaporation of water from a subsurface reservoir. Europa's frozen surface is interspersed with dark and brilliant stripes and curvilinear ridges and grooves that intersect. Spatter cones within certain channels indicate subsurface fluid explosions. The topography is quite flat, with ridge elevations reaching only a few hundred meters at most. Europa possesses the smoothest surface of any solid celestial body analyzed within the solar system. Researchers have detected evidence of sulfur compounds, hydrogen peroxide, and organic molecules on the surface. The primary unresolved inquiry is whether a worldwide ocean of liquid water exists beneath Europa's ice, heated by the discharge of tidal energy within Europa's interior. The potential for such an ocean emerged from Voyager data, and high-resolution Galileo photographs indicated fluid movement at the surface. Furthermore, elucidating Europa's induced magnetic field necessitates the presence of an electrically conductive fluid medium within. This indicates the presence of a saline liquid water layer beneath the surface ice. Should this ocean and its requisite heat source be there, we must recognize the probable existence of at least microbial life forms. Io. When observed through a telescope from Earth, Io exhibits a reddish-orange hue, while the other moons display a neutral coloration. Io's infrared spectrum exhibits no indications of the absorption properties of water ice. Scientists anticipated that Io's surface would differ from that of Jupiter's other moons. Yet the Voyager photos unveiled a terrain more peculiar than imagined. Volcanic fissures, rather than impact craters, punctuate the surface of Io. In 1979, the two Voyager spacecrafts detected 9 erupting volcanoes, but Galileo's closer observations indicated that as many as 300 volcanic vents might be active simultaneously. The silicate lava ejected from the vents is exceedingly hot, about 1900 K, 3000 degrees, 1630 degrees, akin to primordial lavas on early Earth. This extraordinary activity renders Io the most tectonically active entity in the solar system. This volcanism entirely and continuously renews the satellite's surface within a few thousand years. Different allotropes of sulfur are likely responsible for the black, orange, and red regions of the Moon's surface, although solid sulfur dioxide is presumably the primary component of the white parts. The infrared spectrometer on Voyager found sulfur dioxide in gaseous form near an active volcanic plume. But ultraviolet and infrared spectra from Earth orbital and ground-based studies classified it as a solid. These identifications establish the origins of the sulfur and oxygen ions seen in the Jovian magnetosphere, and demonstrate that Io's volcanic activity is the source of its particle torus. The energy driving this volcanic activity requires a distinct explanation, as nuclear heating is inadequate for a body as diminutive as Io. The preferred hypothesis relies on the discovery that the orbital resonances with the other Galilean satellites induce perturbations in Io, resulting in a more eccentric orbit than it would maintain under the sole influence of Jupiter. The tides generated by the gravitational interactions between Io, other satellites, and Jupiter release sufficient energy to explain the observed volcanism. The interior comprises a dense, iron-rich core that likely generates a magnetic field. The interactions of Io with Jupiter's magnetosphere and ionosphere are so intricate that distinguishing the satellite's intrinsic field from the fields generated by surrounding currents has proven challenging. Additional satellites. Amalthea, a little irregularly shaped Jovian moon, named after a character in Greek mythology linked to the infant Jupiter, was the sole other moon sufficiently proximate to the Voyager spacecraft's trajectory for surface details to be discernible. Amalthea orbits Jupiter every 11 hours and 57 minutes, 0.498 Earth days, at a distance of 181,000 km, 112,500 miles, in a roughly circular trajectory, aligned within half a degree of Jupiter's equatorial plane. Images relayed by the Voyager 1 and 2 spacecraft in 1979 and validated by the Galileo orbiter in the late 1990s indicate that Amalthea is an irregular rocky entity with dimensions of 262 x 146 x 134 km, 163 x 91 x 83 miles. Like the Moon, which consistently presents the same hemisphere to Earth, Amalthea rotates synchronously with its orbit around Jupiter, maintaining a constant orientation towards the planet. Amalthea's elongated axis consistently orients toward Jupiter. By assessing Amalthea's gravitational impact on the Galileo spacecraft, researchers established that the Moon possesses an exceptionally low density of 0.9 grams per cubic centimeter, allowing it to float in water. Amalthea is porous, likely due to multiple collisions fragmenting its granite interior. We have also noted low densities for certain inner moons of Saturn, which we ascribe to this factor. Amalthea possesses a dark, reddish surface characterized by impact craters. The leading hemisphere, oriented towards the direction of motion, is approximately 30% brighter than the trailing hemisphere, perhaps due to impacts by small meteoroids that have entered the Jovian system. The proximate volcanically active satellite Io perpetually emits sulfur and sulfur compound particles, presumably accounting for its red hue. The most extensive impact crater on Amalthea is Pan, measuring around 90 kilometers, 55 miles in diameter. The Galileo orbiter provided new photographs of Amalthea and observed the effects of impacts on Thebe and Meti. Like Amalthea, these two moons are tidally locked, consistently presenting the same face to Jupiter, and display a brightness enhancement of roughly 30% on their leading hemispheres. Before the onset of the 21st century, 8 outer moons were identified, consisting of 2 separate orbital groups. The more remote group, Ananke, Calm, Pasiphae, and Sinope, exhibits retrograde orbits around Jupiter. The inner group Leda, Himalaya, Lysithea, and Elara exhibits prograde orbits. For these moons, retrograde motion occurs in the direction contrary to Jupiter's rotation and its orbit around the Sun, but counterclockwise, when observed from above Jupiter's north pole. Conversely, prograde motion aligns with these movements. In 1999, astronomers systematically searched for new Jovian satellites, employing highly sensitive electronic detectors capable of identifying fainter and subsequently, smaller objects. Upon discovering numerous additional outer moons in the subsequent years, they acknowledged that the bifurcation into 2 families was an oversimplification. Over 100 tiny debris, classified into various categories according to their orbits, are likely orbiting Jupiter. Each group seems to have derived from a singular entity, Jupiter ensnared and later disintegrated. The catches likely occurred near Jupiter's formation, when a nebula enveloped the planet, decelerating anything that entered it. The Trojan asteroids may be linked to these little moons. The Ring. During its approach to Jupiter in 1974, the Pioneer 10 spacecraft observed a marked reduction in the density of charged particles, approximately 125,000 km, 78,000 miles, from Jupiter, situated within the orbit of its innermost moon, Tethys. This indicated the potential presence of a moon or a ring of material around the planet at this distance. The initial Voyager spacecraft confirmed the presence of a ring in 1979 upon traversing the planet's equatorial plane, while the subsequent spacecraft captured further images, including a sequence taken in the planet's shadow, directed towards the Sun and the ring. The ring appeared significantly brighter from this vantage point. Most of the ring particles scatter light more effectively in the forward direction than in the reverse direction, toward Earth. Consequently, it was unsurprising that terrestrial observations did not detect the ring before Voyager's findings. The forward scatter indicates that most particles are diminutive, inside the micrometer size range, akin to the specks of dust observed in a sunbeam on Earth, or the minuscule particles on a car windshield, which exhibit a similar optical phenomenon. Photographs acquired by the Galileo spacecraft during 1996-1997 illustrate the intricate configuration of the ring. There exists an outer gossamer ring, imperceptible beyond the orbital radius of the satellite Thebe, 222,000 kilometers, and an inner gossamer ring, confined by the orbit of Amalthea, 181,000 kilometers. The principal ring measures approximately 30 kilometers, 18 miles in thickness, extending from the orbits of Adrastea, 129,000 kilometers, 80,156 miles, and Metis, 128,000 kilometers, 79,535 miles, to an inner boundary at 123,000 kilometers, 76,428 miles. Additionally, a toroidal halo of particles extends from the main ring inward to 92,000 kilometers. The existence of micrometer-sized particles in the ring necessitates a source, and the correlation of the ring limits with the four moons elucidates the source's origin. Micrometeoroids, cometary debris, and maybe volcanically derived material from Io collide with these moons and smaller entities within the primary ring to produce the ring particles. As the planet rotates, the electrically charged particles respond to the oscillation of the Jovian magnetic field. Origin of the Jovian system. The challenge of elucidating the solar system's beginnings includes clarifying the genesis of Jupiter and its moons. Contemporary theories support the sun's and planets' incremental form from a vast cloud of gas and dust, characterized by gravitational instabilities that prompted the cloud's collapse. Due to the planet's substantial hydrogen content and immense mass, it has been conventionally posited that Jupiter originated from the condensation of the primordial solar nebula. This idea suggests that Jupiter ought to possess identical elemental ratios as the Sun. Recent SUNY research suggests that Jupiter's constituent proportions diverge from solar norms. Contemporary models of Jupiter's genesis propose that a solid core, approximately 10 times the mass of Earth, initially formed by the accretion of frozen planetesimals. The core would have generated its own atmosphere as the planetesimals emitted gases during the accretion process. With the increase in core mass, it would have gained the ability to draw gases from the surrounding solar nebula, thereby building the vast hydrogen-helium envelope that forms Jupiter's atmosphere and fluid mantle. The accumulating envelope would have interacted with the outgassed atmosphere in the core. Consequently, relative to solar values, the current enrichment of the predominant heavy elements in this envelope signifies the accumulation of these elements in the core. The Galileo probe's mass spectrometer indicated an almost threefold enrichment of these heavy elements. For this enrichment to encompass volatile substances such as argon and molecular nitrogen, the ice planetesimals must have originated at 30 K, 400 degrees, 240 degrees C, or lower temperatures. The enigma of this occurrence remains, and its elucidation may illuminate the presence of substantial planets near their stars in other planetary systems. It is widely believed that the genesis of Jupiter's inner 8 moons parallels that of the planet itself. Similar to the primordial solar nebula's fragmentation into accreting planetesimals that formed the planets, and a central condensation that became the Sun. The ASU negation of material within a protoplanetary cloud at Jupiter's orbit ultimately resulted in the formation of the planet and its inner moons. The analogy extends further. The elevated temperature during Jupiter's creation seemingly inhibited the condensation of volatile compounds at the proximity of the innermost moons. Consequently, Ganymede and Callisto, the farthest of the 8 inner moons, exemplify the volatile, rich outer bodies within this system. The formation of the numerous small outer moons, characterized by their extreme eccentricities and inclinations, is markedly distinct. They belong to the population of irregular satellites inside the solar system and are presumably captured entities. Their ultimate origin, meanwhile, remains ambiguous. The parent bodies of these moons may have originated in Jupiter's outer nebula, deviated, and then been recovered. Alternatively, they may have formed separately within the solar nebula and then been recaptured. In both scenarios, the capture process caused the disintegration of the parent bodies, leading to the debris recognized today as the outer irregular moons. Continued research on these objects and their potential relatives within the Trojan asteroids may elucidate their origin. Saturn. Unaided eyes may readily observe Saturn in the night sky as a stable point of light, and even a modest telescope can unveil the planet's remarkable rings, rendering it possibly the most exquisite object in the solar system. The Greek god Cronus, a Titan and the progenitor of Zeus, and the Roman god Jupiter are the origins of the name Saturn. Ancient astronomers observed Saturn as the slowest moving planet and the furthest distant from the Sun. Saturn, being 9.5 times further from the Sun than Earth, completes one solar revolution in approximately 30 Earth years. In 1610, the Italian astronomer Galileo was the first to see Saturn using a telescope. Despite observing an anomaly in Saturn's appearance, the limited resolution of his instrument precluded him from discerning the true nature of the planet's rings. Saturn is the second largest planet in the solar system by mass and size, and it ranks 6th in proximity to the Sun. It constitutes over 60% of Jupiter's volume, yet possesses approximately 1/3 of its mass, exhibiting the solar system's lowest mean density, around 70% of water, of any known entity. Saturn would theoretically buoy in a sufficiently vast ocean. Hydrogen predominates the overall chemical makeup of Saturn and Jupiter, akin to stars. Like Jupiter, Saturn's core's immense pressure sustains hydrogen in a fluid metallic form. Nonetheless, Saturn's composition and evolutionary trajectory contrast with those of its larger relatives. Like the other gas giants, Jupiter, Uranus, and Neptune, Saturn possesses large systems of moons and rings, which may offer insights into its origin, evolution, and that of the solar system. Titan is distinguished from other moons by its thick atmosphere, which is more substantial than that of any terrestrial planet, save Venus. A comprehensive understanding of Saturn and numerous other planets is derived from deep space probes. 4 spacecraft have explored the Saturnian system: Pioneer 11 in 1979, Voyagers 1 and 2 in the subsequent 2 years, and Cassini-Huygens commencing in 2004, after an almost 25-year interval. The initial 3 missions were brief flybys, whereas Cassini entered orbit around Saturn for an extended period of research, while its Huygens probe descended through Titan's atmosphere and landed on its surface, marking the first instance of a spacecraft landing on a moon other than Earth's. Saturn revolves around the Sun at an average distance of 887 million miles. Its distance from Earth is consistently no less than approximately 1.2 billion kilometers, 746 million miles, and its phase angle, the angle formed with the Sun and Earth, never surpasses approximately 6 degrees. Saturn consistently seems almost completely lighted from Earth's proximity, a constraint that deep space spacecraft have ultimately surmounted. Similar to Jupiter and the majority of other planets, Saturn possesses a consistent orbit. Specifically, its trajectory around the Sun is prograde, aligned with the Sun's rotation, and exhibits minimal eccentricity, deviation from circularity, and inclination relative to the ecliptic plane of Earth's orbit. In contrast to Jupiter, Saturn's rotational axis is significantly tilted by 26.7 degrees relative to its orbital plane. The axial tilt of Saturn produces seasons similar to those on Earth. However, each season endures for over 7 years. Observers on Earth perceive Saturn's rings, positioned in the plane of its equator, at degrees of inclination, from 0 degrees, edge-on, to almost 30 degrees. The perspective of Saturn's rings undergoes a cycle every 30 years. Observers on Earth can view the illuminated northern side of the rings for approximately 15 years, followed by a similar observation of the illuminated southern side for the subsequent 15 years. The rings are imperceptible during the few moments when Earth traverses the ring plane. Saturn lacks a fixed rotation period. The movements of clouds in its extensive upper atmosphere exhibit diverse durations, ranging from around 10 hours and 10 minutes at the equator to about 30 minutes longer, at latitudes over 40 grand, with significant oscillation. Researchers have determined the rotation period of Saturn's inner core based on its magnetic field, which is thought to emanate from the planet's metallic hydrogen outer core. The direct measurement of the field's rotation is challenging due to its remarkable symmetry around the rotational axis. Radio emissions from Saturn, associated with minor anomalies in the magnetic field, have a duration of 10 hours, 39.4 minutes during the Voyager encounters. This measurement was used as the rotation period of the magnetic field. 25 years later, however, certain Cassini data suggested that the field was revolving, extending a period of 6 to 7 minutes. Variations in rotational period measurements may result from the solar wind. We have utilized the temporal discrepancies between the rotation periods of Saturn's clouds and its interior to approximate wind velocities. Other radio bursts, with durations of around 10 hours and 10 minutes, emanate from lightning within Saturn's atmosphere. Traditionally, we determine the radius and gravity of the 4 gas giants at 1 bar of atmospheric pressure, since their outer layers lack a solid surface. The equatorial diameter of Saturn is 120,536 kilometers, 7,498 miles. In contrast, its polar diameter measures merely 108,728 kilometers, 67,560 miles, or 10% smaller, rendering Saturn the most oblate planet in the solar system. Its oblate form is evident even with a modest telescope. Although Saturn rotates marginally slower than Jupiter, it exhibits greater oblateness due to its rotational acceleration counteracting a bigger proportion of the planet's gravitational force at the equator. The planet's equatorial gravity, measuring 896 centimeter (29.4 physics) per second squared, constitutes merely 74% of its polar gravity. Saturn possesses a mass 95 times that of Earth, while encompassing a volume 766 times larger. Its average density of 0.69 g cm3, 0.4 Oz in 3, is approximately 12% of Earth's density. The equatorial escape velocity of Saturn, encompassing individual atoms and molecules, is around 36 km per second, 80,000 miles per hour, at the 1 bar level, in contrast to Earth's 11.2 km per second, 25,000 miles per hour. This elevated value signifies that Saturn has seen no substantial atmospheric loss since its inception. The atmosphere. From Earth's perspective, Saturn exhibits a predominantly hazy yellow-brown hue. Telescopes and spacecraft imagery disclose a stratified arrangement of cloud layers on the surface. Like other gas giants, Saturn's atmospheric circulation is predominantly characterized by zonal, east-west flow. This is seen as a pattern of brighter and darker cloud bands akin to those of Jupiter, although Saturn's bands exhibit more nuanced coloration and are broader near the equator. The cloud top characteristics exhibit minimal contrast, enabling the Voyager flybys to facilitate an in-depth examination of Saturn's atmospheric circulation. When characterized by the rotation of its magnetic field, Nearly all of Saturn's atmospheric currents, or winds, travel eastward, aligned with the direction of rotation. The eastward flows are far more pronounced in comparison to Cassini's reduced magnetic rotation rate. In latitudes around 2010, the equatorial zone demonstrates a notably vigorous eastward current, reaching a peak velocity near 500 meters per second, 1,800 kilometers, so 100 miles per hour. This feature resembles one on Jupiter but spans twice the latitude and operates at 4 times the speed. In contrast, the most intense winds on Earth are seen in tropical cyclones, in which, in extreme instances, sustained speeds can surpass 67 meters per second, 240 kilometers, 150 miles per hour. The zonal flows exhibit notable symmetry around Saturn's equator, with each flow at a specific northern latitude, typically having a corresponding flow at a comparable southern latitude. At 46 degree N and S, as well as approximately 60 degree N and S, we find robust eastward currents, with relative velocities surpassing 100 meters per second, 360 kilometers, 225 miles per hour. Almost steady westward currents are observed at 40 degree, 55 degree, and 70 degree Ds, N and S within the magnetic field's reference frame. After the Voyager visits, advancements in terrestrial instrumentation facilitated remote observations of Saturn's clouds. These studies, conducted over several years, generally aligned with the comprehensive Voyager measurements of zonal fluxes, validating their temporal stability. High-resolution measurements of Saturn's atmosphere revealed a significant decrease in the velocity of the equatorial jet from 1996 to 2002. Nonetheless, analysis of data from the Cassini orbiter indicates that any reduction in velocity is limited to the outer layers of the atmosphere. The overarching north-south symmetry suggests a possible link between the zonal circulation within the interior. Theoretical modeling of a deep convecting fluid planet like Saturn suggests that differential rotation manifests along cylinders oriented with the planet's average rotation axis. Consequently, a sequence of coaxial cylinders oriented north-south, each revolving at distinct velocities, may constitute Saturn's atmosphere, resulting in the zonal jets detected at the surface. A significant discontinuity within Saturn, such as the core, may disrupt the continuity of the cylinders. Saturn's atmosphere has numerous smaller-scale characteristics similar to those observed on Jupiter, including red, brown, and white patches, bands, eddies, and vortices that fluctuate rapidly. Moreover, Saturn's atmosphere, while exhibiting a far more subdued look, is less dynamic than Jupiter's on a microscale. During September-November 1990, a remarkable anomaly transpired as a substantial, pale-hued storm system emerged near the equator, extended to about 20,000 kilometers, 12,400 miles, in size, and ultimately encircled the equator before dissipating. Observers have noted storms comparable in magnitude to the Great White Spot, analogous to Jupiter's Great Red Spot, occurring around every 30 years since the late 19th century. This approximates Saturn's orbital period of 29.4 years, indicating that these storms are seasonal occurrences. Preliminary data analysis from the Voyager spacecraft revealed that the planet's atmosphere comprises 91% molecular hydrogen by mass, making it the most hydrogen-dominant environment in the solar system. Indirect observations indicate that helium, comprising an additional 6%, is less prevalent than hydrogen compared to a gas with a composition identical to our Sun. Should hydrogen, helium, and other elements exist in the same ratios as in the Sun's atmosphere, Saturn's atmosphere would comprise around 71% hydrogen and 28% helium by mass. Some theories indicate that helium may have segregated from Saturn's outer layers. However, current research suggests that the Voyager analysis may have overestimated the helium proportion in Saturn's atmosphere, perhaps aligning it more closely with the solar value. Other significant chemicals detected in Saturn's atmosphere include methane and ammonia, which are 2 to 5 times more prevalent in hydrogen than a solar composition gas. Hydrogen sulfide and water, regarded as primary components of the deeper atmosphere, have yet to be discovered. Minor compounds identified spectroscopically from Earth comprise phosphine, carbon monoxide, and germane. Such molecules would remain undetectable in a hydrogen-rich atmosphere at chemical equilibrium. They may be non-equilibrium results of reactions occurring at elevated pressure and temperature in Saturn's deep atmosphere underneath the visible clouds. We detect many non-equilibrium hydrocarbons in Saturn's stratosphere, such as acetylene, ethane, propane, and methylacetylene. Photochemical reactions can generate all of the aforementioned. Astronomers on Earth have examined the refraction of starlight and radio waves from spacecraft traversing Saturn's atmosphere to obtain data on atmospheric temperature, at depths corresponding to pressures ranging from 1/1,000,000th of a bar to 1.3 bars. Minor chemical molecules condense in the hydrogen-rich atmosphere, forming Saturn's observable cloud layer. Photochemical reactions generate particles suspended in the atmosphere at pressures of 20 to 70 millibars, whereas the primary cloud formation occurs at pressure levels over 400 millibars, with solid ammonia crystals believed to constitute the uppermost cloud layer. We anticipate that the base of the ammonia cloud deck will be located at a depth of approximately 1.7 bars, where the ammonia crystals disintegrate into hydrogen gas and abruptly vanish. Our understanding of the deeper layers of clouds is primarily derived from chemical models simulating the behavior of molecules in a gas with a composition akin to that of the Sun, informed by the temperature-pressure profile of Saturn's atmosphere. The bases of deeper cloud layers are located at 4.7 bars, ammonium hydrosulfide crystals, and 10.9 bars, water ice crystals with aqueous ammonia droplets. While all the aforementioned clouds would be colorless in their pure form, Saturn's real clouds exhibit diverse yellow, brown, and red hues. Chemical impurities, especially those with phosphorus, seem to generate these colors. Despite the exceedingly high pressures in the deepest layers of Saturn's atmosphere, the minimum atmospheric temperature of 82 K is insufficient for molecular hydrogen to coexist as a gas and a liquid in equilibrium. Consequently, there is no clear demarcation between the upper atmosphere, where hydrogen primarily exists as a gas, and the lower atmosphere, which resembles a liquid. In contrast to Earth's tropopause, Saturn's troposphere does not conclude at a solid boundary, but seemingly stretches tens of thousands of kilometers beneath the observable clouds, achieving temperatures in the thousands of kelvins and pressures exceeding 1,000,000 bars. The magnetic field and magnetosphere. Like a basic dipole or bar magnet, Saturn's magnetic field aligns its north-south axis within 1 degrooms of its rotating axis, with the magnetic dipole's center near the planet's core. The magnetic polarity of Saturn's field, akin to that of Jupiter, is inverted compared to Earth's current field. Specifically, the field lines emanate from Saturn's northern hemisphere and re-enter the southern hemisphere. Additionally, Saturn's magnetic moment is approximately 600 times that of Earth, while Jupiter's magnetic moment is 20,000 times greater than Earth's. Saturn's magnetosphere, a teardrop-shaped zone surrounding the planet, is mostly influenced by its magnetic field rather than interplanetary magnetic fields, affecting the behavior of charged particles, predominantly from the Sun. The convex side of the teardrop faces the Sun, creating a boundary or magnetopause with the solar wind at approximately 20 Saturn radii, 1/200,000 kilometers, 750,000 miles, from the planet's center, though this distance varies significantly due to fluctuations in solar wind pressure. A vast magnetotail spreads to great distances on the opposite side of Saturn, distorting the magnetosphere. Similar to the magnetospheres of Earth and Jupiter, Saturn's inner magnetosphere retains a consistent population of very energetic charged particles, predominantly protons, which traverse spiral trajectories along magnetic field lines. These particles create rings around Saturn, analogous to the Van Allen belts on Earth. In contrast to Earth and Jupiter, the absorption of particles onto the surfaces of solid planets inside the field lines significantly reduces Saturn's population of charged particles. Voyager data revealed the presence of holes in the particle populations along field lines that cross the rings and the orbits of moons within the magnetosphere. Titan and Hyperion, Saturn's moons, orbit near the minimal dimensions of the magnetosphere and periodically traverse the magnetopores, venturing beyond Saturn's magnetosphere. Charged particles in Saturn's outer magnetosphere clash with neutral atoms in Titan's upper atmosphere, energizing them and resulting in atmospheric erosion. The Cassini orbiter detected a halo of very energetic atoms. Saturn exhibits ultraviolet auroras, generated by the collision of energetic particles from the magnetosphere with atomic and molecular hydrogen in its polar atmosphere. In the 1990s, the Hubble Space Telescope, in orbit around Earth, obtained ultraviolet photos of Saturn. The late 1990s and early 21st century successfully captured the auroral rings surrounding the poles. These provided clear proof of the pronounced symmetry of Saturn's magnetic field and elucidated the manner in which the auroras react to the solar wind and the Sun's magnetic field. The low, mean density of Saturn suggests that its primary composition is mostly hydrogen. Under the planet's circumstances, hydrogen exists as a liquid rather than a gas at pressures exceeding around 1 kilobar, which corresponds to a depth of 1,000 kilometers, 600 miles, beneath the clouds. At this level, the temperature is approximately 1,000 K, 1,340 degrees, 730 degrees. Molecular hydrogen, even in its liquid state, is a very compressible substance, and to get Saturn's average density of 0.69 g cm3, 0.4 Oz in 3, pressures above 1 megabar are necessary. This transpires at 20,000 kilokilometer, 12,500 miles beneath the clouds, almost one-third of the distance to the planet's core. Examining Saturn's non-spherically symmetrical gravitational field yields insights into its internal structure. The planet's rapid rotation and low mean density cause distortion in both its physical shape and gravitational field. The shape of the field can be accurately determined by analyzing its influence on the trajectories of adjacent spacecraft and the configuration of certain elements of Saturn's rings. Mass distribution within Saturn's core, as opposed to its outer envelope, directly influences the extent of distortion. The distortion analysis indicates that Saturn is considerably more centrally condensed than Jupiter, thus possessing a markedly greater quantity of material denser than hydrogen in its core. The central portions of Saturn comprise roughly 50% hydrogen by mass, whereas Jupiter's central regions contain about 67% hydrogen. We anticipate that fluid molecular hydrogen will experience a significant phase transition to a fluid metallic state, akin to a molten alkali metal such as lithium, at approximately 2 megabars of pressure and a temperature of around 6,000 K, 10,300 degrees F, 5,730 degrees C. This transition occurs around midway between Saturn's cloud tops and its core. Data from the planet's gravitational field indicates that the center metallic zone possesses a density far greater than that of a mixture of pure hydrogen with solar proportions of helium. The surplus helium accumulated from the planet's outer layers may partially explain the heightened density. Moreover, existing data may not ascertain the exact distribution of material denser than hydrogen and helium, which could possess a total mass up to 30 times that of Earth within Saturn. A compact central core is expected to aggregate a rock and ice composition of 10 to 20 Earth masses. If sluggish circulation currents exist in Saturn's outer core of fluid metallic hydrogen, as anticipated from heat ascending to the surface and denser components descending due to gravity, then sufficient dynamo activity is present to generate the planet's magnetic field. Consequently, the identical mechanism responsible for generating Earth's magnetic field also accounts for Saturn's. The dynamo theory posits that the deep field, located near the core in the dynamo zone, may exhibit considerable irregularity. Conversely, spacecraft examine the exterior region of the field, which exhibits considerable regularity, with a dipole axis approximately aligned with the rotational axis. Theories propose that a non-convecting, electrically conducting zone, rotating relative to the field lines, enhances the symmetry of the magnetic field lines around the rotational axis before their intersection with the surface. Intense electric currents within the conductive core may account for the significant alteration in the magnetic field rotation period seen during the last 25 years. Saturn emits approximately twice the energy into space than it absorbs from the Sun, predominantly at infrared wavelengths ranging from 20 to 100 micrometers, 0.008 to 0.04 inches. This disparity signifies that Saturn, like Jupiter, has an interior heat source. The internal energy production of Saturn is analogous to that of Jupiter for each kilogram of mass. Nevertheless, due to Saturn's inferior mass compared to Jupiter, it possessed a diminished total energy content during the formation of both planets. Its radiation at Jupiter's level indicates that some of its energy derives from an alternative source. A thermal evolution estimate indicates that Saturn may have formed with a core with 10-20 Earth masses, accumulated from the accretion of ice-rich planetesimals. Additionally, a substantial quantity of gaseous hydrogen and helium from the primordial solar nebula would have amassed due to gravitational collapse. Scientists propose that Jupiter underwent a comparable formation process, though it assimilated a significantly greater gas. Both planets elevated the gas to elevated temperatures, several tens of thousands of kelvins, during the acquisition process. Jupiter's present internal energy production can be comprehended as the residual cooling of a formerly heated planet over the solar system's lifespan of around 4.6 billion years. For Saturn, implementing this method suggests that the planet's energy output should have declined below the current level approximately 2 billion years ago. Helium has theoretically been precipitating from its solution in hydrogen, and its steady descent has released supplementary gravitational energy. Potential energy converts into the kinetic energy of droplet motion, as helium segregates into droplets within the metallic phase of hydrogen and descends to lower levels. Friction subsequently attenuates this motion, converting it into heat, radiating into space, augmenting Saturn's internal heat supply. Jupiter is thought to have undergone a similar process, albeit far less, due to its warmer interior and higher helium concentration. The Voyager's identification of a notable helium deficiency in Saturn's atmosphere initially corroborated this notion. However, it has since encountered skepticism. Although seemingly two separate entities, Saturn's rings and moons constitute a sophisticated system of objects characterized by highly interconnected structures, dynamics, and evolutionary processes. The trajectories of the innermost known satellites are situated within or adjacent to the outermost rings, with newly discovered moons remaining integrated into the ring formation. The ring system has numerous small moons, varying from dust particles to objects the size of cars and houses, each in its own orbit around Saturn. Due to the challenge of differentiating between the largest ring particles and the smallest moons, accurately ascertaining the number of moons orbiting Saturn may be unfeasible. In 1610, Galileo's initial observations of Saturn through a rudimentary telescope led him to declare that Saturn is not a singular star, but rather a conglomerate of three bodies that nearly contact one another, remain stationary relative to each other, and are aligned linearly along the zodiac, with the central body being 3 times larger than the outer ones. 2 years later, he was bewildered that the image in his telescope had transformed into a singular object. Earth had traversed Saturn's ring plane, and when viewed edge-on, the rings had virtually vanished. Subsequent observations revealed to Galileo that the intriguing lateral appendages had reappeared. He never inferred that the appendages constituted a disk surrounding the planet. In 1655, the Dutch scientist Christian Huygens commenced his observations of Saturn using an enhanced telescope, ultimately discerning the actual configuration of the rings and the significant inclination of the ring plane relative to Saturn's orbit. He maintained, however, that the rings constituted a singular solid disk of considerable thickness. In 1675, the Italian-born French astronomer Gian Domenico Cassini discovered a significant gap, now referred to as the Cassini division, within the ring system, undermining the notion of a solid ring. Subsequently, in 1789, the French mathematician and scientist Pierre-Simon Laplace proposed a theory suggesting that the rings comprised numerous smaller particles. In 1857, Scottish physicist James Clerk Maxwell analytically established that the rings could only be stable if they consisted of many microscopic particles, a conclusion corroborated almost 40 years later by American astronomer James Keeler. It is recognized that although Saturn's rings are vast, they are remarkably thin. The principal rings possess a diameter of 270,000 tuonsundskiin and 170,000 miles, yet their thickness does not surpass 100 meters, 330 feet, and their cumulative mass is around 3x 10^19 kilograms, 6.6x 10^19 pounds, roughly equivalent to the mass of Saturn's moon Mimas. The ring system extends almost 1,000,000 kilometers, 600,000 miles, when accounting for the feeble outer rings. Like other gas giants, Saturn's principal rings are situated within the traditional Roche limit. The optimal distance for a somewhat large moon to approach the center of its more massive planetary progenitor before tidal forces disintegrate, it is 2.44 Saturn radii, 147,000 kilometers, 9,300 miles. Tidal forces, conversely, inhibit small bodies within the Roche limit from coalescing into bigger entities. The limit pertains solely to things bound by gravitational attraction. It does not constrain the stability of a very small body whose molecular cohesiveness supersedes the tidal forces that may disintegrate it. Consequently, small moons and artificial satellites measuring tens of kilometers or smaller can endure eternally under the Roche limit. While the particles constituting Saturn's rings are not immediately observable, we can infer their size distribution based on their influence on the scattering of light and radio signals transmitted via the rings from celestial bodies and spacecraft. This investigation demonstrates a wide and continuous range of particle sizes, extending from centimeters to several meters, with larger particles being far less numerous than smaller ones. The distribution corresponds with the anticipated result of successive collisions and fragmentation of originally larger entities. In certain regions of the rings, where collisions seem to occur more frequently, smaller, dust-sized particles are found. Nonetheless, these possess brief lifespans due to various loss mechanisms. The smaller grains of clouds seemingly obtain electric charges, engage with Saturn's magnetic field, and present as dynamic, wedge-shaped spokes radiating across the plane of the rings. Although spokes were frequently observed during the Voyager encounters, Cassini's first orbits did not detect them, possibly indicating the influence of a different solar angle on the formation of charged particles. Substantial bodies called ring moons, measuring several kilometers in diameter, may be situated within the principal rings, Nevertheless, only a limited number have been identified. Evidence indicates that the opposing influences of gravity, collisions, and fluctuating orbital velocity within the thick rings perpetually generate and annihilate ephemeral rubble pile moons. The rings effectively reflect sunlight, and a spectroscopic examination of the reflected light indicates the existence of water ice. Consequently, it is conceivable that the disintegration of a moon comparable in size and composition to Mimas generated the primary rings. Due to the rings' irreversible dispersion caused by particle collisions and the absence of a known mechanism to maintain their current configuration indefinitely, many planetary scientists hypothesize that the theorized breakup leading to ring formation occurred relatively recently, possibly within the last tens of millions of years. The primary ring system exhibits structures across several scales, from the three extensive major rings, C, B, and A, in order of increasing distance from Saturn, observable from Earth, to numerous individual component ringlets with widths measuring in kilometers. The structures have afforded scientists an advantageous domain for examining gravitational resonances and the cumulative influences of numerous tiny particles in proximity. Although scientists have theoretically elucidated numerous structures, many remain cryptic, and a comprehensive system synthesis is still absent. Saturn's ring system may serve as an analogue for the primordial disk of particles from which the planets originated. Thus, comprehending its dynamics and evolution has significant consequences for the solar system's genesis. The optical depth of the rings, as a function of distance from Saturn, delineates their structure. A medium, including a cloud, a planet's atmosphere, or an area of particles in space, absorbs electromagnetic radiation quantified as optical depth. Consequently, it functions as a measure of the medium's average density. A perfectly transparent medium possesses an optical depth of 0. When its density escalates, its numerical value correspondingly grows. Optical depth is contingent upon the radiation wavelength and the characteristics of the medium. Radio wavelengths of several centimeters and longer in Saturn's rings are predominantly unimpeded by the tiniest ring particles, resulting in reduced optical depths compared to visible wavelengths. The B ring is the most luminous, widest, and most substantial of the rings. It ranges from 1.52 to 1.95 Saturn radii and exhibits optical depths between 0.4 and 2.5. The specific values are contingent upon both the distance from Saturn and the wavelength of light. The equatorial radius of Saturn measures 60,268 kilometers, 37,449 miles. The Cassini division, the most notable gap in the principal rings, visually distinguishes it from the outer major ring, the A ring. The Cassini division, situated between 1.95 and 2.02 Saturn radii and containing particles, displays intricate changes in optical depth, averaging 0.1. The A ring spans from 2.02 to 2.27 Saturn radii and exhibits optical depths ranging from 0.4 to 1.0. The C ring, sometimes known as the Kuiper ring, is the third major ring located interior to the B ring, situated around 1.23 to 1.52 Saturn radii, with optical depths close to 0.1. Within the C ring, at distances of 1.11 to 1.23 Saturn radii, resides the exceedingly sparse D ring, which exerts no discernible influence on starlight or radio waves traversing it and is observable solely in reflected light. The narrow F ring is outside the A ring at 2.33 Saturn radii. Cassini's discoveries indicate that the F ring is a complex structure resembling a tightly wound spiral. A thin band of material, likely ejected by the inner moon atlas, is located between the A and F rings along its orbit. The fragile G ring, situated around 2.8 Saturn radii away and possessing an optical depth of merely 0.0 Seoul-G1, is positioned even farther out. Images from Voyager dimly reveal the elusive G ring, attributed to its impact on charged particles within Saturn's magnetosphere. Images captured by Cassini in 2008 disclosed the existence of a diminutive moon within the G-ring, designated Aegaeon, measuring approximately 0.5 kilometers, 0.3 miles in diameter. This moon may be one of the progenitor bodies of the G-ring. The outermost identified ring, the exceptionally wide and diffuse E-ring, spans from 3 to 8 Saturn radii. Cassini's observations have verified that ice particles emanating from geysers, a form of ice volcanism, or cryovolcanism, in a thermally active area, a hotspot, near the south pole of Enceladus, constitute the E-ring. Like Jupiter's rings, Saturn's rings beyond the A-ring predominantly comprise minute particles incessantly released by its moons. Significant voids exist in the optical depth distribution inside the principal ring sections. Prominent astronomers linked to Saturn research have had significant gaps named in their honor. Alongside the Cassini division, the gaps include the Colombo, Maxwell, Bond, and Dawes gaps. 129, 145, 147, and 150 Saturn radii, respectively. Within the C-ring, the Huygens gap, 195 Saturn radii, at the outer boundary of the B-ring, the Encke gap, 2.21 Saturn radii, in the outer region of the A-ring, and the Keeler gap, 2.26 Saturn radii, situated near the outer edge of the A-ring. Among these gaps, only Encke was recognized before the spacecraft explored Saturn. After the Voyager missions, scientists hypothesized that a moon of 10 kilometers, 6 miles in diameter, circling within the gap zone, could exclude particles from an area to create a gap. Voyager photos identified the moon pan within the Encke gap in 1990, and Cassini images subsequently captured it again. Images from Cassini in 2005 identified the expected moon, Daphnis, located within the Keeler gap. Analogous moons may be present within the Huygens and Maxwell gaps. Other ideas suggest that a moon with an orbit significantly internal or external to a ring can create a gap in that area via orbital resonance. Resonance occurs when the orbital periods of the moon and the ring particles exhibit a ratio of whole numbers. In such instances, a certain ring particle will consistently approach the moon at identical points in its orbit, and gravitational disturbances to its trajectory will accumulate over time, ultimately compelling the particle to deviate from exact resonance. When the moon orbits beyond the ring, it acquires angular momentum from the resonant ring particles, subsequently generating a tightly wound spiral density wave within the ring, which can eventually create a gap if the resonance is sufficiently strong. The boundary region at the B-ring's outer margin and the Cassini division's inner edge exhibit a 2.1 resonance with Mimas, indicating that Mimas's orbital period is twice that of the ring particles at that radius. The resonance indicates that the border is not entirely circular, exhibiting radius deviations that provide a two-lobed configuration. The position of this border plainly illustrates the resonance's impact on the inner edge of the Cassini division. Yet, our comprehension of the division's overall structure still needs to be completed. The co-orbital moons Janus and Epimetheus have a 7.6 resonance with the outer boundary of the A-ring, characterized by 7 scalloped lobes. The effects of analogous resonances are seen throughout the ring system, yet several related characteristics remain inexplicable. A substantial augmentation in the count of identified moons and resonances is necessary to elucidate the myriad ringlets and intricate structures within Saturn's ring system. Satellites. Saturn has over 60 recognized moons. Among the initial 18 moons of Saturn identified, all but the somewhat more remote moon, Phoebe, revolve around 3.6 million kilometers, 2.2 million miles, of Saturn. Before the 20th century, astronomers identified 9 moons, with a radius greater than 100 kilometers, 60 miles. Whereas an examination of Voyager photos revealed the remaining moons in the early 1980s. The photos captured by the Cassini spacecraft started to disclose multiple supplementary inner moons, little entities with radii ranging from 3 to 4 kilometers, 1.9 to 2.5 miles. All inner moons exhibit regularity, possessing prograde, low inclination, and low eccentricity orbits relative to the planet. Analogous to the formation of planets surrounding the Sun from the primordial solar nebula, scientists postulate that Saturn's 8 largest moons originated from a protoplanetary disk of material along the planet's equatorial plane. A secondary outer group of moons can be found beyond around 11 million kilometers, 6.8 million miles. Their orbits exhibit significant eccentricities and inclinations. Around 2/3 orbit Saturn retrogradely, moving contrary to the planet's rotation. Except Phoebe, their orbital radii are under 20 kilometers, 12 miles. In 2000, initiatives were initiated to implement novel electronic detection techniques to identify certain objects from Earth, while Cassini uncovered further ones. These external bodies are not primordial moons, but rather captured entities or their remnants. Certain atypical and enigmatic features of the orbital and rotational dynamics of Saturn's moons arise from their interactions with the rings. It is claimed that the 3 diminutive moons, Janus, Epimetheus, and Pandora, situated at the outer periphery of the primary ring system, have acquired angular momentum from ring particles via collective gravitational interactions. This technique would mitigate the dispersion of rings resulting from collisions among ring particles and propel these moons into more expansive orbits. Due to the diminutive size of the moons, researchers have encountered challenges in identifying a mechanism that could sustain this process over the solar system's history without displacing the moons significantly from their present locations. The distinctness of the outer border of the primary ring system and the current trajectories of inner moons like Atlas are enigmatic, suggesting that the existing ring system is far younger than Saturn itself. Scientists refer to Pandora and her closest moon, Prometheus, as shepherd moons because of their impact on ring particles. Pioneer 11 identified the 2 planets orbiting on either side of the slender F ring just 1 year prior during Voyager 1's flyby. The gravitational interactions of the moons with the F ring provide a shepherding effect, restricting the ring's particles to a restricted area. Prometheus, the inner shepherd, imparts angular momentum to the ring particles, propelling the ring outward and inward, whereas Pandora, the outer shepherd, absorbs angular momentum from the ring particles, driving the ring inward and outward. Cassini recorded a remarkable video of this phenomenon, in which the shepherd moons extract intricate wave-like bands of particles from the F ring as they traverse it. The term shepherd is frequently employed to denote any moon that utilizes gravitational forces to limit the range of a ring. Thus, in this broader context, moons like Janus and Epimetheus, which exhibit ring effects as previously mentioned, together with gap-creating moons such as Pan, are also classified as shepherds. Janus and Epimetheus are co-orbital satellites, possessing an identical average orbit. Every few years they approach closely, gravitationally interacting, such that one transfers angular momentum to the other, resulting in the latter ascending to a marginally higher orbit, and the former descending to a slightly lower orbit. The process is reiterated in the reverse direction during the subsequent close approach. Tethys and Dione possess co-orbital satellites. However, due to their greater mass compared to these co-orbiters, there is negligible exchange of angular momentum. Tethys's 2 co-orbiters, Callisto and Calypso, occupy stable Lagrangian locations along Tethys's orbit, leading and trailing by 60 degrees, similar to the Trojan asteroids in Jupiter's orbit. On average, Dione's Trojan companions, Helene and Polydeuces, precede and follow it by 60 degrees, respectively. Multiple pairs of moons exist in stable dynamic resonances, meaning that the members of each pair periodically pass one another in their orbits, interacting gravitationally in a manner that maintains the consistency of these encounters. In this resonance, the orbital periods of a duo of moons approximate a ratio of tiny integers. The orbital periods of Hyperion and the closer Titan, at 2128 and 1594 days respectively, exhibit a ratio of 4.3, indicating that Titan completes 4 circles around Saturn when Hyperion completes 3. Titan and Hyperion approach each other closely at Hyperion's apoapsis, the most distant point of its eccentric orbit. The periodic shoves compel Hyperion into a relatively extended eccentric orbit, as Titan, possessing over 50 times Hyperion's mass, consistently imparts the greatest momentum to the smaller moon at identical locations in its orbit. The moon's orbital periods, Dione and Enceladus, and Tethys and Mimas, exhibit a 2.1 ratio. Resonances between pairs of moons can induce significant orbital eccentricities, making them potentially crucial in the geological evolution of the affected planets. Tidal interactions between Saturn and her proximal moons, cyclic deformations in one body induced by the gravitational pull of the other, typically diminish the moon's eccentricity and synchronize their rotation to match that of Saturn. This synchronous rotating state is prevalent in the solar system, as demonstrated by the Earth's moon and several of Jupiter's proximal moons. The interior deformation of a moon orbiting its planet is dynamic. It undergoes cyclical movement, producing heat via internal friction. When a moon achieves synchronous rotation, it consistently presents the same hemisphere to the planet, maintaining fixed forward and backward hemispheres in its orbit. The deformation becomes immobile inside the moon's reference frame, and frictional heating ceases to occur. Nevertheless, if resonance induces a moon into an eccentric orbit, even when in synchronous rotation, it undergoes tidal interaction. As it periodically moves further from and closer to its planet, the resulting dynamic deformation generates internal heat. Jupiter's Io exemplifies the most spectacular instance of such a moon. While current calculations suggest that the existing tides on Saturn's moons are not a substantial heating source, this may have been different historically. Moreover, Enceladus's thermally active Tiger Stripe region currently serves as the source of icy material for the diffuse E-ring surrounding it. We must ascertain the origin of the region's thermal activity, probably attributable to tidal deformation. Hyperion is a remarkable anomaly in which tidal forces compel moons to achieve synchronized rotation. The orbital eccentricity and irregular shape of Hyperion, atypical for a body of its size, have resulted in a complex interplay between its spin and orbital angular momentum. This interaction is mathematically characterized as chaotic. Despite the transient Voyager contacts indicating that Hyperion rotates non-synchronously for approximately 13 days, the application of chaos theory to Voyager data and later terrestrial lunar observations reveals that it is, in fact, tumbling erratically. Hyperion is the sole celestial body in the solar system exhibiting chaotic rotation. Titan. Titan is Saturn's largest moon and the sole moon in the solar system, recognized for possessing clouds and a substantial atmosphere. In 1655, the Dutch scientist Christian Huygens discovered Titan through a telescope, marking it the first planetary satellite following Jupiter's 4 Galilean moons. The moon is named after Greek mythology Titans, including Cronus, identified with the Roman god Saturn, and his 11 siblings. Titan presents as a largely uniform brownish-red sphere when observed through an Earth-based telescope, its surface consistently obscured by a dense haze. It exceeds Mercury in size and surpasses Pluto in mass. In certain respects, it resembles a planet more than a conventional moon. Titan circles Saturn at an average distance of 1,221,850 kilometers, 759,220 miles, completing one round in 15.94 Earth days. It completes one rotation on its axis for each revolution, indicating synchronous rotation. Titan consistently presents the same face toward Saturn and maintains the same leading face in its orbit. The solid body of Titan has a diameter of 5,150 km, 3,200 miles, approximately 120 miles larger. Titan is roughly 150 km, 75 miles, smaller than Ganymede, Jupiter's biggest moon and the largest moon in the solar system. Nonetheless, when accounting for its extensive atmosphere spanning hundreds of kilometers, Titan's dimensions far exceed those of Ganymede. Titan's mean density of 1.8 GCM3, 1.1 Aussie in 3, suggests that its interior comprises a combination of stony and frozen substances, perhaps incorporating ammonia, water, and methane, potentially featuring liquid layers beneath a solid crust predominantly of water ice. A rocky core may be located at the center, extending to 80% of the whole radius. Titan's bulk qualities resemble other substantial icy moons in the outer solar system, including Jupiter's Ganymede and Callisto, and Neptune's largest moon, Triton. The atmosphere of Titan. Dutch-American astronomer Gerard P. Kuiper first identified Titan's atmosphere spectroscopically in 1944, discovering evidence of methane's absorption of sunlight. Nevertheless, investigations into the refraction of radio waves in the atmosphere conducted during Voyager 1's flyby in 1980 indicated that methane molecules constitute merely a small percentage of the total molecular composition, while the predominant molecules remain undetectable in visible light spectra. A comparative analysis of infrared and radio data from Voyager indicated that the atmospheric constituents possess a mean molecular weight of 28.6 atomic mass units. Consequently, Voyager accurately identified molecular nitrogen, mean molecular weight 28, as the most probable primary component, although some atomic argon, mean molecular weight 36, may also be present. Voyager identified more components in Titan's atmosphere by absorbing ultraviolet light from the Sun, including molecular hydrogen and several carbon-containing compounds. These are thought to be caused by solar UV radiation interacting with methane and nitrogen at elevated altitudes. These encompass carbon monoxide, carbon dioxide, and the organic gases, ethane, propane, acetylene, ethylene, hydrogen cyanide, diacetylene, methylacetylene, cyanoacetylene, and cyanogen, all detected in trace quantities. Framework. Titan's atmosphere resembles that of Earth in its nitrogen gas composition and surface pressure, around 1.5 bars, which is 50% greater than Earth's sea level pressure. Nevertheless, the Moon's atmosphere is far cooler, with a surface temperature of 94 K, 290 degrees, 179 degrees, and lacking free oxygen. A troposphere similar to Earth's extends from Titan's surface to an elevation of 42 kilometers, 26 miles, when a minimum temperature of 71 K, 332 degrees, 202 degrees C is attained. The lack of nitrogen clouds results from temperatures persistently exceeding the nitrogen condensation point. Preliminary observations from the Cassini-Huygens mission, which commenced exploring the Saturnian system in 2004, indicate that methane is a modest, yet significant atmospheric component, potentially comparable to water vapor in Earth's troposphere. Approximately 5% of the air molecules at Titan's surface consist of methane, with the proportion diminishing with height. Earth's lower atmosphere generally comprises approximately 1% water vapor. Upon its initial encounter with Titan, Cassini detected a significant eruption of methane cumulus clouds in the southern polar area of Titan. Indirect evidence suggests that methane rain occasionally precipitates near the surface. Unlike Earth, Titan does not possess a liquid methane ocean, as it would necessitate an atmospheric mixing ratio of 12%, which contradicts observed data. Titan possesses a tenuous atmospheric layer with a rather uniform temperature above the troposphere, succeeded by a vast stratosphere extending from 50 to 200 kilometers, 30 to 120 miles, in elevation, where temperatures progressively rise with altitude, reaching a peak of 160 to 180 K, 172 to 136 degramb, 113 to 93 degrees C. Research on the refraction of starlight in Titan's upper atmosphere indicates that temperatures persist within this range up to 450 kilometers, 280 miles. While spacecraft investigations of solar ultraviolet light transmission reveal comparable values at much greater altitudes. Titan's haze, aerosols of complex organic substances, continuously generated by solar UV radiation interacting with the nitrogen-methane atmosphere, possibly constitute Titan's veiling haze. These minute particles absorb sunlight and contribute to the deep brownish-red hue. These particles are remarkably ubiquitous in Titan's atmosphere, maintaining significant density even at 300 kilometer, 200 miles heights, and pressures below 1 millibar. The Huygens entrance probe detected haze particles while descending through the troposphere to a height of around 30 kilometers, 20 miles. Particle dimensions range from 0.1 micrometers, 0.0004 inches. Evidence indicates that the density of these particles experiences seasonal variations, increasing in Titan's summer hemisphere due to solar light. The solar heating of particle layers generates a temperature inversion layer in Titan's stratosphere, inhibiting the dissipation of the smog layer by convection. The haze particles are thought to gradually descend through the atmosphere and gather on Titan's surface. Titan's past has resulted in a continuous layer of organic substances enveloping the entire surface to a depth of at least several hundred meters. Titan's atmospheric composition and intricate organic compounds indicate that the Moon could serve as a laboratory for examining the varieties of organic molecules and the chemical processes that contributed to the emergence of life on Earth 4 billion years ago. Titan's nitrogen-rich atmosphere, akin to Earth's, is considered secondary rather than primordial. It likely originated from the photochemical breakdown of ammonia, a prevalent ice in the outer solar system, into molecular nitrogen and hydrogen. The capacity of a sizable moon like Titan to maintain a significant atmosphere for billions of years relies on a precise equilibrium among surface gravity, atmospheric molecular weight, and solar radiation. An increased gravitational pull between the Moon and an air molecule leads to an extended retention duration. In contrast, a warmer atmosphere heightens the molecule's probability of escaping into space. The Galilean moons of Jupiter and Earth's moon are too warm to keep significant gases, whereas the chilly Titan and the sufficiently large Earth have preserved nitrogen molecules. Neither Titan nor Earth has preserved the lighter hydrogen molecule. The Expanse. Before the Cassini-Huygens mission, scant information existed regarding Titan's surface. Due to the Moon's haze being partially transparent to near-infrared light, previous telescopic investigations utilizing this characteristic revealed that the surface is not homogeneous. Images captured in near-infrared wavelengths by the Hubble Space Telescope in 1994 unveiled a luminous continent-sized area, subsequently designated as Xanadu Regio, on Titan's leading hemisphere. The radar frequencies that penetrated the haze enabled Earth and the Cassini probe to identify this location. While orbiting Saturn, the Cassini spacecraft conducted multiple observations during a series of close flybys of Titan starting in late 2004. On January 14, 2005, the Huygens entry probe became the inaugural spacecraft to alight on a planetary surface in the outer solar system. It conducted several physical and chemical analyses of Titan's atmosphere, and relayed high-resolution photos during its parachute descent. The Cassini-Huygens mission demonstrated that Titan's surface is relatively youthful in planetary terms, with only a limited number of significant impact craters. Wind and probable rain, akin to liquid methane, shaped Titan's surface in a manner comparable to Earth's. Channels called rivers are frequently lined with dark hydrocarbon deposits, occasionally traversing faults and often including extensive tributary systems. Cat scratches, elongated dark structures oriented east-west that extend for hundreds of kilometers, may represent dunes composed of dark particle matter. Contrary to anticipations of lakes and oceans, we have definitively observed no surface liquids on Titan. Mimas. Mimas is the smallest and innermost of Saturn's principal regular moons. The English astronomer William Herschel discovered it in 1789 and named it after a giant from Greek mythology, Gigantes. Mimas has a diameter of around 400 km, 250 miles, and orbits the planet in a prograde, almost circular trajectory at an average distance of 185,520 kilometers, 277 miles. Due to tidal interactions with Saturn, the Moon exhibits synchronous rotation with its orbital motion, consistently presenting the same hemisphere towards Saturn while leading with that hemisphere in its orbit. The average density of Mimas is merely 1.1 times that of water, and its surface exhibits features of water frost. These facts contribute to the assertion that Mimas predominantly comprises ice. The surface is luminous and extensively characterized by profound, bowl-shaped impact craters. The depth of the craters results from insufficient surface gravity, which is evidently inadequate to induce slumping. Despite its small size, Mimas has signs of resurfacing, potentially due to the partial melting of its glacial covering. The most significant characteristic is the Herschel crater, which has a diameter of 130 kilometers, 80 miles, and is located in the center of the leading hemisphere. The crater's outside walls rise 5 kilometers, 3 miles. Its bottom descends 10 kilometers, 6 miles, and the central peak reaches 6 kilometers, 4 miles. Herschel is among the greatest impact structures about the size of the celestial body known in the solar system. Mimas is in an orbital resonance with the more remote Saturnian moon Tethys. Its 22.6-hour orbit around Saturn is half that of Tethys, resulting in the two bodies consistently approaching each other on the same side of Saturn. This resonance is not coincidental. It likely originated via a gradual process, such as the deceleration of Saturn's rotation, due to tidal friction, which, according to the principle of conservation of momentum, resulted in the expansion of the orbits of both moons, with Mimas seeing a greater increase than Tethys over geological time. Mimas is in orbital resonance with multiple recognized formations inside Saturn's ring system. The resonant interactions between ring particles and the Moon delineate the inner boundary of the Cassini divide, a notable gap characterized by reduced particle density within the primary rings, exhibiting an orbital period approximately half that of Mimas. Additional ring orbits that resonate with Mimas display bending waves, tightly coiled spiral waves of ring material shifted upward or downward from the ring plane. Enceladus. Enceladus is the second closest of Saturn's principal regular moons, and the most luminous of all its moons. The English astronomer William Herschel found it in 1789, naming it after one of the giants from Greek mythology, Gigantes. Enceladus has a diameter of approximately 500 kilometers, 310 miles, and circles Saturn in a prograde, almost circular trajectory, at an average distance of 238,020 kilometers, 147,199 miles. Its average density is merely 30% more than that of water, suggesting it is composed of at least 50% water ice. The surface of Enceladus exhibits a higher albedo than freshly fallen snow. Images from Voyager revealed a scarcity of huge craters. Smooth, crater-free regions and broad ridged plains provided compelling evidence of relatively recent internal activity, perhaps occurring within the last 100 million years, resulting in substantial melting and resurfacing. Spectral measurements from Cassini indicate that the surface of Enceladus is predominantly composed of water ice. No information regarding Enceladus was available before the US spacecraft Voyager 2 flyby in 1981. The probe, coming within 87,140 kilometers, 54,146 miles, captured photos indicating that Enceladus possesses a complex geological structure, having experienced 5 separate evolutionary phases. In 2005, Cassini initiated a sequence of close flybys of Enceladus, approaching within 200 kilometers, 125 miles. These observations validated that certain regions of the Moon exhibit contemporary geological activity, characterized by significantly elevated heat flow, surpassing expectations based solely on solar heating, and the ejection of water vapor and ice from geysers, a phenomenon known as cryovolcanism, particularly prominent in the southern polar area. The Moon's southern polar hotspot registers a temperature of 140 K, 208 degrees, 133 degrees, and features perplexing geological formations called tiger stripes. Numerous craterless regions may be merely 100 million years old, indicating that surface segments have been melting and refreezing in the recent geological past, implying that Enceladus may possess multiple active zones. Enceladus's ongoing activity generates Saturn's E-ring, a delicate ring composed of micrometer-sized water ice particles formed from vapor expelled by the geysers. The particles are most concentrated near Enceladus's orbit and resemble the cloud of orbital particles expelled from Jupiter's volcanically active moon, Io. Cryovolcanic eruptions consistently renew the orbital lifespans of E-ring particles, potentially as brief as 10,000 years. Enceladus ejects water ice particles that contribute to the E-ring at approximately 1,000 metric tons annually. Like Europa, the potential presence of liquid water in Enceladus renders it a favorable habitat for life. Enceladus's 33-hour orbit around Saturn is half that of the more distant moon Dione, indicating an orbital resonance between the two celestial bodies. In some conditions, such resonance may result in significant tidal heating for the inner moons involved. Nonetheless, comprehensive calculations are necessary to demonstrate how this mechanism may produce sufficient heating to explain the ongoing activity within Enceladus. Tethys. A notable rift encircles the majority of Tethys. The Italian-born French astronomer Gian Domenico Cassini found Tethys in 1684 and named it after a titan from Greek mythology. Tethys possesses a diameter of 1,060 kilometers, 659 miles, and a density of 1.0 g cm3, 0.58 Oz in 3, equivalent to that of water, suggesting it is comprised entirely of ice. It orbits Saturn in a prograde, circular trajectory at 294,260 kilometers, 183,090 miles, within the planet's extensive, tenuous E-ring. It entails an orbital resonance with the proximal moon, Mimas, so Tethys completes one 45-hour orbit for every 2 orbits of Mimas. Tethys exhibits synchronous rotation with its orbital period, maintaining a constant orientation towards Saturn while presenting the same face throughout its trajectory. 2 diminutive moons, Callisto and Calypso, named after the daughters of Titans, accompany Tethys, preserving gravitationally stable locations along its orbit, akin to Jupiter's Trojan asteroids. Callisto is positioned 60 degrees ahead of Tethys. Calypso is positioned 60 degrees behind. Tethys exhibits minimal indications of internal activity. Its most remarkable characteristic is Ithaca Chasma, a vast fissure several kilometers deep that spans 3/4 of the moon's circumference and constitutes 5 to 10% of its surface area. Scientists hypothesize that the extensively cratered ridges surrounding the feature signify the chasm's primordial geological development. History commenced when the water within its interior froze and expanded. A second significant characteristic is the Odysseus crater, which spans 400 kilometers, 250 miles, in diameter and contains a prominent central peak. The elevated density of impact craters on Tethys indicates that the surface is archaic. Nonetheless, the surface has significant reflectivity, particularly on Tethys's leading hemisphere, which is atypical for geologically ancient surfaces. Planetary scientists hypothesize that the deposition of micrometer-sized ice particles from Saturn's E-ring, in which Tethys is significantly immersed, influences surface brightness distribution. The finding that numerous craters on Tethys possess brilliant flaws, in contrast to the dark flawed craters on Saturn's moon Hyperion, which orbits at a greater distance from Tethys, and the E-ring, is presented as proof. Dione. Gian Domenico Cassini, a French astronomer of Italian heritage, found Dione in 1684 and named it after a daughter of the Titan Oceanus in Greek mythology. Dione possesses a diameter of 1,120 kilometers, 696 miles, and orbits Saturn on a prograde, almost circular trajectory, at an average distance of 377,400 kilometers, 234,500 miles, situated within the outer region of Saturn's sparse E-ring. Two little moons, Helene and Polydeuces, named after figures from Greek mythology, join Dione in its orbit. Helene, with a diameter of around 30 kilometers, 20 miles, occupies a gravitationally stable position 60 degrees in advance of Dione. Polydeuces, possessing a diameter less than 50% of Helene's, trails Dione by 60 degrees, despite displaying considerable fluctuations from its average location. We can juxtapose the trajectories of these diminutive partner moons with those of Jupiter's Trojan asteroids. Tidal interactions with Saturn have decelerated Dione's rotation, resulting in synchronous rotation with its orbital motion, consistently presenting the same hemisphere to the planet while leading with the same hemisphere in its orbit. The surface of Dione exhibits remarkable brightness differences, with the trailing hemisphere typically darker than the leading hemisphere. Dione's elevated average reflectivity indicates a surface abundant in geologically freshwater ice. The moon's low density, 1.5 times that of water, aligns with a bulk composition of approximately equal proportions of ice and rock. Dione is extensively marked by impact craters, with their density and size distribution indicating a geological age of 4 billion years. Conversely, in certain regions, the crater density is diminished, indicating that the moon may have undergone significant ice melting and resurfacing. New ice particles from the E-ring may continuously accumulate on Dione's surface. The illuminated prominent hemisphere contains most of Dione's craters. Many luminous linear structures constitute a polygonal network, fragmenting the opposing hemisphere. Episodic tectonic activity may have induced some brilliant characteristics linked to linear troughs and ridges. Images from the Voyager spacecraft unveil delicate formations, thought to represent deposits of recondensed volatile substances emanating from linear fissures in Dione's core. Nevertheless, high-resolution photos from the Cassini mission reveal no indication of such activity. Despite indications of a significant effect around the core of the linear network on the trailing hemisphere, the asymmetry of the moon's surface remains ambiguous. Like several objects in orbit around Saturn, Dione participates in an orbital resonance. Specifically, its 66-hour orbit around Saturn is twice that of the closer moon Enceladus. This link has been suggested as a cause of the significant tidal heating observed in Enceladus. However, the specifics of this mechanism require further elucidation. Rhea. Rhea is Saturn's second-largest moon, following Titan. The Italian-born French astronomer Gian Domenico Cassini found it in 1672 and designated it after a Titan from Greek mythology. Rhea possesses a diameter of 1,528 kilometers, 949 miles, and orbits Saturn in a prograde, almost circular trajectory, at an average distance of 527,040 kilometers, 327,490 miles, with an orbital period of around 4.52 Earth days. The density of Rhea, 1.3 times that of water, indicates that the Moon is predominantly composed of ice. Moreover, infrared spectral data indicate a mostly water frost surface. Like most of Saturn's significant moons, Rhea exhibits synchronous rotation with its orbital period, maintaining a constant hemisphere directed towards Saturn and the same hemisphere advancing in its orbit. The surface of Rhea exhibits significant reflectivity, while considerable regional differences are evident. Rhea is comparable to Saturn's moon, Iapetus, in size and density. Nevertheless, its surface brightness distribution is contrary to Iapetus's and is less pronounced. In this respect, it is akin to its adjacent moon, Dione. Its leading hemisphere is luminous and densely cratered, while its trailing hemisphere is darker, featuring dazzling, wispy streaks, a scarcity of craters, and indications of resurfacing. At Saturn's distance from the Sun, frozen water and other volatile materials solidify, exhibiting mechanical properties akin to rock, hence preserving impact craters. Thus, Rhea's luminous cratered surface closely resembles the extensively cratered Mercury Highlands or Earth's moon. Rhea is the most extensively cratered moon of Saturn, and its surface's reflecting characteristics suggest it possesses significant porosity, akin to the moon's impact-generated regolith. Researchers have detected luminous stripes on the darker, trailing hemisphere of Rhea. The probable causes of the streaks are tectonic activity, faulting, or the release of volatiles, such as water or methane, through fissures and their subsequent deposition on the surface. During its orbit around Saturn, the prominent hemisphere of Rhea showcases a strikingly luminous crater with enormous bright rays radiating across much of the surface, akin to the renowned rayed lunar crater Tycho.
Hyperion.
Hyperion is distinguished by its lack of a consistent rotation period. Instead, it exhibits a seemingly erratic tumbling motion inside its orbit. In 1848, American astronomers William Bond and George Bond made the discovery, but English astronomer William Lassell independently identified it. It was called after a Titan from Greek mythology. Hyperion orbits Saturn every 21.3 Earth days in a prograde direction at a distance of 1,481 kilometers, 300 miles, situated between the orbits of the Moon's Titan and Iapetus. Hyperion's orbit is distinctive due to its eccentricity, elongation, while being inclined less than half a degree from the plane of Saturn's equator. The closer moon, Titan, completes 4 circles around Saturn for every 3 orbits of Hyperion, establishing a 4.3 dynamic resonance, with the 2 moons nearing each other most closely when Hyperion is at its apogee. Under these circumstances, Titan, the somewhat more massive entity, imparts periodic gravitational perturbations on Hyperion, compelling it into a relatively eccentric orbit. Another characteristic of Hyperion is its non-spherical morphology. It is occasionally likened to a big hamburger patty, with dimensions of 370 x 280 x 225 kilometers, 230 x 174 x 140 miles. It is the largest recognized moon with a distinctly uneven morphology. The reflectivity of 30%, which is moderately elevated, aligns with some water frost on its surface. Hyperion exhibits a reddish tint, akin to the mysterious dark regions on the remote moon Iapetus. Hyperion's average density is approximately 50% that of water ice, indicating that the moon's interior could be a sparse collection of ice fragments interspersed with cavities. This structure may explain the notable spongy appearance of certain regions of Hyperion's cratered surface, as observed in photos from the Cassini spacecraft. Due to Hyperion's irregular shape and eccentric orbit, it fails to sustain a stable rotation around a fixed axis. Hyperion exhibits a unique chaotic rotation, altering its rotational properties on periods as brief as 1 month, distinguishing it from all known celestial bodies in the solar system. Theoretically, Hyperion can revolve seemingly regularly for periods spanning several thousand years, succeeded by equally protracted phases of chaotic tumbling, rendering its rotation at any specific moment entirely unpredictable. Iapetus. Iapetus, the outermost of Saturn's principal regular moons, is remarkable due to its significant disparity in surface brightness. Gian Domenico Cassini, a French astronomer of Italian heritage, discovered it in 1671 and named it after a Titan from Greek mythology. Iapetus possesses a radius of 718 kilometers, 446 miles, and completes an orbit around Saturn every 79.3 Earth days, at a distance of 561,300 kilometers, 2,229 miles. A bulk density of 1.0 grams per cubic centimeter indicates that ice constitutes most of its composition. The inner moons of Saturn orbit around 1 degree of Saturn's equatorial plane. However, in the orbit of Iapetus and beyond, the gravitational effect of Saturn's equatorial bulge diminishes, allowing for greater orbital inclinations. Researchers propose that Iapetus's average inclination of 15 degrees is a vestige of the tilt from the now extinct gaseous disk that created Saturn's principal regular moons. Tidal forces with Saturn have synced Iapetus's rotation with its orbital period. Consequently, the Moon consistently presents the same hemisphere to Saturn and perpetually orients the same face over its orbital trajectory. Notably, the leading hemisphere exhibits profound darkness, reflecting merely a small fraction of the incident sunlight, whereas the trailing hemisphere demonstrates up to 10-fold greater reflectivity. The reflectance at the poles is far greater. Iapetus has the most pronounced variations in luminosity among all recognized celestial bodies. The solar system. Cassini noted that when Iapetus orbited Saturn, he could observe it from one side but not the other, and he accurately hypothesized the cause of this phenomenon. Despite the United States, the Voyager spacecraft flybys disclosed impact craters exclusively on the bright trailing side of Iapetus, whereas subsequent high-resolution photographs from the Cassini mission also revealed craters on the leading side. The surface composition on the illuminated side is predominantly pure water ice, potentially combined with other types of ice. The opaque layer of intricate organic compounds, along with iron-rich minerals modified by water, covers the crimson surface of the dark side. The disparity in reflectivity results from dark material, consisting of particles sourced from the Saturnian system, accumulating on the Moon's leading hemisphere. This material absorbs more sunlight, heating the region sufficiently to induce substantial sublimation of water ice over geological time. The water vapor then condenses on the trailing hemisphere and solidifies. The Cassini mission captured images of a notably slender ridge surrounding a significant portion of Iapetus's equator. Models indicate that the movements of a thin, active ice lithosphere created this ridge when the deeper layers of the Moon were heated. Conversely, the Moon's observable impact basins and other topographical features often necessitate a thicker lithosphere. The Moon's swift temperature fluctuations in its initial million years likely shaped most of its features. Phoebe. Phoebe is a medium-sized, irregular satellite of Saturn. In 1899, American astronomer William Henry Pickering identified it on photographic plates and designated it after a Titan from Greek mythology. Phoebe is approximately spherical, with a diameter of 220 kilometers, 136 miles, and an average distance from Saturn of 12,952,000 km, 8,050,000 miles. much exceeding that of Saturn's other principal moons. It requires roughly 1.5 Earth years to orbit Saturn once. Its orbit is markedly eccentric, retrograde, and sharply tilted relative to the plane of Saturn's rings and normal moons. Phoebe's surface exhibits significant reflectivity variations, but it is predominantly dark. Infrared spectral measurements indicate the existence of water ice particles intermingled with black material, akin to the carbonaceous substances seen on primordial C-class asteroids. Certain lunar craters exhibit indications of alternating strata of luminous and dark substances. Phoebe possesses a mean density approximately 1.6 times greater than pure water ice, exceeding the density of most of Saturn's significant icy moons. According to this discovery and Phoebe's anomalous orbital characteristics, several scientists propose that the Moon did not originate in orbit around Saturn, but developed in a remote orbit from the Sun, where thermal conditions and carbon-oxygen chemistry varied. Resolving objects on Saturn, smaller than a few thousand kilometers, is unfeasible, even under optimal telescopic viewing circumstances from Earth's surface. Consequently, the intricate details of the rings and atmosphere were predominantly unrecognized before spacecraft studies. In 1837, the German astronomer Johann Franz Encke documented the Encke gap within the A-ring. For nearly a century, it remained questionable until American astronomer Harold Reitzimer validated it in 1978 by employing observations from an eclipse of the moon Iapetus by the rings to enhance standard Earth-based resolution. Contemporary investigations of Saturn from Earth proximity depend on diverse specialized telescopic methodologies. Infrared spectroscopy of the rings, atmosphere, and moons has provided significant insights into their composition and thermal equilibrium. We get spatial resolution of the rings and atmospheric structures on a kilometer scale by detecting light from luminous stars that transit behind the planet as viewed from Earth. 1989, Saturn and Titan occulted the luminous star 28 Sagittari, enabling scientists to examine ring and atmosphere structures with unprecedented detail since the Voyager missions. Surface-based telescopes and the Hubble Space Telescope effectively detected the 1990 emergence of the Great White Spot in Saturn's atmosphere, free from the distortions of Earth's atmosphere. In 1995, Earth's passage through the ring plane allowed for an edge-on perspective, directly assessing the ring's thickness and accurately calculating Saturn's rotational axis precession rate. Pioneer 11 was the inaugural spacecraft to explore Saturn, the United States. It was one of two probes launched in the early 1970s to explore Jupiter. Although retargeting was not included in the initial objective, mission scientists utilized Pioneer 11's proximity to Jupiter's gravitational field to modify the spacecraft's course, enabling a successful flyby of Saturn. In 1979, Pioneer 11 traversed Saturn's ring plane at merely 38,000 km, 24,000 miles from the A ring, and approached within 21,000 km, 13,000 miles of its atmosphere. The US Voyager 1 and Voyager 2, the twin spacecraft, were initially launched toward Jupiter in 1977. The US Voyager 1 and 2 spacecraft were equipped with sophisticated imaging apparatus, specifically engineered for multi-planet flybys, and to achieve distinct scientific goals at each location. Like Pioneer 11, Voyagers 1 and 2 utilized Jupiter's gravitational influence in gravity-assist maneuvers to alter their trajectories towards Saturn, which they reached in 1980 and 1981. The two spacecraft transmitted thousands of photos of Saturn, its rings, and its moons. The United States, European, and Italian space agencies launched the Cassini-Huygens mission in 1997. The spacecraft followed a convoluted trajectory featuring two gravity-assist flybys of Venus and flybys of Earth and Jupiter, ultimately reaching the Saturnian system in mid-2004. The interplanetary craft, loaded with propellants, weighed over 6 metric tons and was among the largest, most costly, and most intricate constructed then. The mission included a Saturn orbiter, Cassini, intended for an extensive study of the planet, its rings and moons, and a probe, Huygens, which parachuted through Titan's atmosphere to achieve a solid surface touchdown in early 2005. Huygens conveyed measurements and photographs to Cassini for around 3 hours throughout its fall, and from the surface, transmitting them to Earth scientists. Uranus. Uranus, the 7th planet from the Sun, is located beyond Saturn, and is the least massive of the solar system's 4 big or Jovian planets, which include Jupiter, Saturn, and Neptune. At its peak luminosity, Uranus is discernible to the naked eye as a blue-green speck of light. Uranus is named after the personification of the heavens and is both the son and consort of Gaia in Greek mythology. A telescope identified Uranus in 1781, rendering it the inaugural planet not acknowledged in prehistoric eras. The telescope observed Uranus multiple times throughout the past century, but regarded it merely as another star. Its average distance from the Sun is around 2.9 billion kilometers, 1.8 billion miles, exceeding 19 times the distance from Earth, and it never comes closer to Earth than roughly 2.7 billion kilometers, 1.7 billion miles. Uranus, akin to the other gas giants, predominantly comprises hydrogen, helium, water, and many volatile substances, attributable to its comparatively low density, about 1.3 times that of water, and substantial size, 4 times Earth's radius. Therefore, it does not possess a solid surface. Methane in the atmosphere of Uranus absorbs red wavelengths of sunlight, imparting a blue-green hue to the planet. Most planets revolve at an angle about perpendicular to their orbits around the Sun. Uranus's axis is approximately parallel to its orbital plane, resulting in the planet rotating virtually on its side, with its poles alternating in orientation toward the Sun as it orbits. Moreover, the rotation axis and the planet's center substantially incline the axis of the planet's magnetic field. Uranus possesses about 20 moons, 5 of which are comparatively large, along with a system of slender rings. The Voyager 2 probe of the United States conducted the sole spacecraft visit to Uranus in 1986. Before that time, astronomers had limited knowledge of the planet, as its distance from Earth complicates examining its visible surface, even with the most advanced telescopes. Earth-based efforts to ascertain a fundamental attribute such as the planetary rotation time yielded significantly varying results, spanning from 24 to 13 hours, until Voyager 2 ultimately determined a 17.24-hour rotation period for the interior of Uranus. Following Voyager's visit, advancements in terrestrial observational technologies have enhanced our understanding of the Uranian system. At Uranus's distance from the Sun, the planet requires little over 84 Earth years, approximately the duration of a human lifespan, to complete one orbit. The orbit's eccentricity is low, indicating minimal deviation from a perfect circle, and the orbital inclination to the ecliptic, which is the plane of Earth's orbit and almost that of the solar system, is less than rounded. The solar system planets typically exhibit low orbital eccentricity and inclination, with the notable exceptions of Mercury and Pluto. Researchers assert that collisions and gaseous drag dissipated energy from the orbits during planetary formation, diminishing the eccentricities and inclinations to their current values. Consequently, Uranus coalesced with the other planets shortly after the Sun's formation, some 4.6 billion years ago. Uranus and its next neighbor Neptune, the subsequent planet from the Sun, are virtually identical in size. At the atmospheric pressure of 1 bar, corresponding to Earth's sea level pressure, Uranus's equatorial radius of 559 quadrant 15,882 miles exceeds Neptune's by 3.2%. However, Uranus possesses merely 85% of Neptune's mass, resulting in a markedly lower density. The disparity in their bulk densities, 1.285 and 1.64 grams per cubic centimeter respectively, indicates a fundamental distinction in composition and interior structure. Despite Uranus and Neptune being considerably larger than the terrestrial planets, their radii are less than half that of the biggest planets, Jupiter and Saturn. The spin axis of Uranus is not perpendicular to the ecliptic, resulting in one pole oriented above and the other below it. The phrases above and below denote the same sides of the ecliptic as Earth's north and south poles, respectively. International agreements describe a planet's north pole as the pole above the ecliptic, irrespective of its rotational direction. According to this description, Uranus rotates clockwise or retrogradely around its north pole, contrasting with the prograde rotation of Earth and the majority of other planets. During Voyager 2's flyby of Uranus in 1986, the North Pole was shrouded in darkness, while the Sun was nearly positioned precisely above the South Pole. In 42 years, or half of a Uranian year, the Sun will be positioned nearly directly overhead at the North Pole. The dominant hypothesis posits that the extreme axial tilt occurred during the concluding phases of planetary accretion, when entities comparable in size to current planets engaged in a series of cataclysmic collisions, resulting in Uranus's lateral orientation. An alternative hypothesis posits that a Mars-sized moon orbiting Uranus in a retrograde manner ultimately collided with the planet, causing it to tilt on its axis. Voyager 2 identified radio wave emissions with a rotation period of 17.24 hours, emanating from charged particles confined within the planet's magnetic field. Subsequent direct measurements of the field indicated a tilt of 58.6 degram relative to the rotation axis, with a corresponding rotation period of 17.24 hours. We hypothesize that the field emanates from the electrically conductive interior of the planet. The rapid rotation induces oblateness, flattening the planet's poles, wherein the polar radius is approximately 2.3% less than the equatorial radius. Atmospheric winds induce the rotation of cloud patterns on the planet's visible surface, with periods varying from 18 hours near the equator to a little over 14 hours at higher latitudes. The atmosphere. The primary components of the Uranian atmosphere are molecular hydrogen and atomic helium. The planet's clouds diffuse sunlight from Earth, enabling the detection of hydrogen. The refraction of Voyager 2's radio signal by the atmosphere when the spacecraft crossed behind the planet established the helium-to-hydrogen ratio. Helium constitutes 15% of the entire count of hydrogen molecules and helium atoms, corresponding to 26% by mass of the overall quantity of hydrogen and helium. These values align with the Sun and exceed those of Jupiter's and Saturn's atmospheres. It is assumed that all 4 big planets acquired identical ratios of hydrogen and helium throughout their formation, with Jupiter and Saturn undergoing some helium sedimentation towards their cores. Theoretical research indicates that the mechanisms responsible for this settling do not function on less massive planets such as Uranus and Neptune. Methane has significant absorption in the near-infrared wavelengths and predominates in that segment of the reflected light spectrum, while being merely 2.3% of the total number of molecules. Astronomers obtained this estimate of methane abundance by analyzing Voyager 2's radio transmissions, which penetrated atmospheric levels where the methane-to-hydrogen ratio is expected to remain constant. If this consistency is typical of the planet, the carbon-to-hydrogen ratio of Uranus is 24 times greater than that of the Sun. Methane, CH4, consists of 1 carbon atom and 4 hydrogen atoms. The elevated carbon-to-hydrogen ratio signifies an increased presence of oxygen, nitrogen, and sulfur relative to solar values. These elements are linked to molecules of water, ammonia, and hydrogen sulfide, which are thought to condense from clouds at altitudes below the visible section of the atmosphere. Radio data from Earth indicate a diminishing presence of ammonia molecules in the atmosphere. This may be due to the prevalence of hydrogen sulfide, which combines with ammonia to form cloud particles of ammonium hydrosulfide. The UV spectrometer on Voyager identified minimal quantities of acetylene and ethane. These gases are byproducts of methane, which dissociates upon exposure to ultraviolet light from the sun in the high atmosphere. Uranus emits energy equivalent to an ideal, fully absorbing surface at 59.1 kelvins, K 353 degree E, 214 degree AC. The radiation temperature corresponds to the physical temperature of the atmosphere at a pressure of approximately 0.4 bar. Temperature diminishes with declining pressure, specifically with ascending altitude, up to the 70 millibar level, where it reaches approximately 52 K, 366 degree, 221 degree C, the lowest temperature in Uranus's atmosphere. Above this point, the temperature increases once again, attaining 750 K, 890 degree, 480 degree in the exosphere. The uppermost layer of the atmosphere located 1.1 Uranian radii from the planetary center, where pressures approximate a trillionth of a bar. We must ascertain the origin of elevated exospheric temperatures, including UV absorption, electron bombardment, and the gas's incapacity to emit at infrared wavelengths. Voyager 2 quantified the horizontal fluctuation of air temperature across 2 extensive altitude ranges, 60-200 millibars and 500 to 1000 millibars. The pole-to-pole fluctuation in both ranges was minimal, under 1 K, 1.8 degree Gemev, 1 degree Kreisnes, despite one pole being oriented towards the sun during the flyby. The deep atmosphere's effective horizontal heat transport and substantial heat storage capacity account for this absence of global variation. Despite Uranus's seemingly featureless appearance, extreme contrast-enhanced photos from Voyager 2 and subsequent terrestrial investigations disclose faint cloud bands aligned parallel to the equator. The analogous zonal flow governs the atmospheric circulation of Jupiter and Saturn, whose rotational axes exhibit somewhat less tilt than Uranus's, resulting in markedly distinct seasonal variations in solar light. The planet's rotation, rather than the absorbed sunlight distribution, governs the cloud's patterns. The Coriolis force, resulting from rotation, causes moving material on a rotating planet to look deflected to the right or left, depending on whether one is in the northern or southern hemisphere. Consequently, Uranus resembles an inverted variant of Jupiter or Saturn in terms of cloud patterns. Wind is the movement of the atmosphere about the rotating planet. At elevated latitudes on Uranus, this relative velocity aligns with the planet's rotation. At equatorial latitudes, relative motion occurs in the contrary direction. Uranus is analogous to Earth in this respect. These directions are east and west on Earth, whereas the broader phrases are prograde and retrograde. The winds on Uranus are significantly more powerful than those on Earth. The wind velocity is 720 kilometers, 450 miles, per hour prograde, at a latitude of 55 degrees S, and 400 kilometers, 250 miles, per hour retrograde at the equator. The equatorial winds of Neptune are retrograde, whereas those of Jupiter and Saturn are retrograde. No adequate theory exists to elucidate these disparities. Uranus lacks significant spots like Jupiter's enduring Great Red Spot or Neptune's Great Dark Spot. which was detected by Voyager 2 in 1989. Voyager's measurements of Uranus's wind profile were derived from merely 4 small locations, exhibiting a visible contrast of only 2 to 3% compared to the surrounding atmosphere. The marks likely signify atmospheric storms, as the gas giants lack solid surfaces. Uranus appears to possess the fewest storms among the large planets for reasons that need to be clarified. The magnetic field and magnetosphere. Convection currents within the electrically conductive interior of Uranus, similar to those of other gas giants, produce a magnetic field. The dipole field, akin to that of a diminutive yet powerful bar magnet, exhibits a strength of 0.23 Gauss on its equatorial plane at a distance equivalent to 1 Uranian equatorial radius from the center. A standard magnetic compass indicates the counterclockwise rotating pole, corresponding to Earth's north pole, as the magnetic field's polarity aligns with the current geomagnetic field. The dipole axis is inclined at an angle of 58.6 degrees about the planet's rotation axis, which is markedly higher than that of Earth, 11.5 degrees, Jupiter, 9.6 degrees, and Saturn, less than 1 degree. The radius of Uranus, around 8,000 km, 5,000 miles, displaces the magnetic center from the planet's core by 31%. The displacement primarily occurs along the rotational axis towards the North Pole. The magnetic field is atypical due to its inclination and displacement, and the very substantial dimensions of its minor components. The quick attenuation of small-scale components of a field above the electrically conductive zone indicates that the field originates at shallow depths within the planet. Consequently, the interior of Uranus must exhibit electrical conductivity nearer to the surface compared to Jupiter, Saturn, and Earth. This conclusion aligns with the established understanding of Uranus's interior composition, which predominantly consists of water, methane, and ammonia, to correspond with the planet's typical density. Water and ammonia break down into cations and anions, which are electrically conductive at comparatively low pressures and temperatures. Fluid dynamics within the conductive layers produce the magnetic field on Uranus. Nevertheless, these layers are shallower compared to those on Jupiter, Saturn, and Earth. Like other planets possessing magnetic fields, Uranus's field deflects the solar wind, a stream of charged particles from the Sun. The planetary magnetosphere, a vast spatial zone, including charged particles tethered to the magnetic field, envelopes the planet and extends downstream. On the upwind side, oriented towards the Sun, the magnetopause, the demarcation between the magnetosphere and the solar wind, is 18 Uranian radii, 460,000 km to $286,000 miles, from the planet's core. The particles confined within the Uranian magnetosphere consist of protons and electrons, suggesting that the planet's upper atmosphere provides most of the material. No evidence exists for helium, potentially sourced from the solar wind, or heavier ions, which may derive from the Uranian moons. The largest moons of Uranus orbit within the magnetosphere, thereby absorbing certain trapped particles. The particles adhere to the magnetic field lines, reducing the number of trapped particles traversing a moon's orbit compared to adjacent field lines. Like Jupiter and Saturn, charged particles from the Uranian magnetosphere impact the upper atmosphere, resulting in auroras. Auroral heating hardly accounts for the elevated temperature of Uranus's exosphere. Despite having a lower density than Jupiter, Uranus possesses a greater fraction of elements heavier than hydrogen and helium. Jupiter's superior mass, by a factor of 22, results in an enhanced gravitational pull, leading to more self-compression than Uranus. This supplementary compression contributes to Jupiter's mass density. If Uranus has material proportions identical to Jupiter's, its density would be markedly reduced. Various hypotheses suggested for the interior of Uranus postulate differing proportions of rock, silicates and metals, ices, water, methane and ammonia, and gases, mostly hydrogen and helium. Under the elevated temperatures and pressures present in the massive planets, the ices will exist as liquids. To align with the bulk density statistics, the mass of rock and ice must represent approximately 80% of Uranus's total mass, in contrast to 10% for Jupiter and 2% for a composition resembling the Sun. All models depict Uranus as a fluid planet, where the gaseous upper atmosphere progressively transitions into the liquid interior. The pressure in the planet's core is around 5 megabars. Scientists have gained deeper insight into the interior by comparing a model's response to centrifugal forces from the planet's rotation with the real measurements obtained from Voyager 2. Voyager 2 articulated this response regarding the planet's oblateness. Researchers can deduce the internal density distribution of the planet by assessing the extent of polar flattening and correlating it with the rotational velocity. Among two planets possessing identical mass and bulk density, the planet with a greater concentration of mass at its center would have reduced flattening due to rotation. Before the Voyager expedition, it wasn't easy to choose models featuring discrete layers of rock, ice, and gas, compared to those with homogeneously mixed ice and gas. The significant oblateness and relatively slow rotation of Uranus, as observed by Voyager, suggests that the ice and gas are thoroughly mixed, indicating a small or non-existent rocky core. The superior fit of the mixed model of Uranus to data, compared to the layered model, may provide insights into the planet's genesis. The mixed model suggests that large, solid objects were continuously captured by a giant planet that already possessed significant quantities of gas, rather than indicating a process where Uranus formed from a rock-ice core that later acquired gas from the solar nebula. Unlike the other three large planets, Uranus does not emit a significant quantity of surplus internal heat. The overall heat output is ascertained from the planet's quantified infrared emissions, whereas the heat input is derived from the proportion of incident sunlight that is absorbed, meaning it is not reflected back into space. The energy ratio for Uranus ranges from 1.00 to 114, indicating that its internal energy source provides, at most, 14% more energy than the solar input. The corresponding ratios for the other gas giants surpass 1.7. The little terrestrial planets, Mercury, Venus, Earth, and Mars, produce comparatively minimal internal heat. For instance, the heat flow from Earth's interior is approximately 1/10,000th of the solar energy it gets. It is essential to comprehend the reasons behind Uranus's minimal internal heat production compared to the other Jovian planets. Due to planetary accretion converting gravitational energy into heat, all planets must have initially been heated. Throughout the solar system's history, Earth and other smaller celestial bodies have dissipated most of their primordial heat. Nevertheless, due to their substantial mass and frigid surfaces, the large planets retain heat effectively and emit it weakly. Consequently, we anticipate they will preserve a substantial amount of their formation heat, which persists in dissipating today. Random occurrences, such as collisions with substantial celestial bodies encountered by certain planets during their creation, along with the consequent variations in internal structure, provide one explanation for the disparities observed among the huge planets, including the unusual thermal emissions of Uranus. Uranus is encircled by a minimum of 10 slender rings and has 27 identified moons. Every particle within the rings functions as a miniature moon in its respective orbit. The rings are nearest the planet. Several small moons orbit slightly beyond the rings. The largest moons orbit further away, and additional small moons orbit at much greater distances. The orbits of the outermost group of moons are eccentric and significantly inclined to the equatorial plane of Uranus. The remaining moons and the rings are fundamentally coplanar with the equator. The 5 biggest moons of Uranus have radii ranging from around 240 to 800 kilometers, 150 to 500 miles. Telescopic observations from Earth resulted in the identification of all 5, with 4 discoveries made before the 20th century. In 1985-86, Voyager 2 identified 10 small inner moons. Estimates indicate their radius spans from 10 to 80 km, 6 to 50 miles, while their orbital distance from the planet varies between 49,800 and 86,000 kilometers, 31,000 to 53,500 miles. The innermost moon, Cordelia, orbits immediately within the outermost rings, Lambda and Epsilon. Voyager captured views of an 11th little inner moon, Perdita, adjacent to Belinda's orbit. Nonetheless, it was unrecognized in the photographs until 1999, with confirmation occurring only in 2003. In 2003, observations from Earth identified 2 further inner moons, Cupid, located near Belinda's orbit, and Mab, situated near Puck's orbit. All 18 aforementioned bodies exhibit normal, prograde, low inclination, and low eccentricity orbit about the planet. Commencing in 1997, Earth identified 9 little outer moons, approximately within the same size parameters as the Voyager discoveries. Except for one, all these irregular satellites orbit retrogradely, possessing very elliptical orbits that are significantly inclined relative to the planet's equator. Their average distances from the planet range from 4 million to 21 million kilometers, 2.5 million to 13 million miles, 7 to 36 times the distance of the outermost known normal moon, Oberon. Uranus presumably acquired the orbits of the irregular moons after the planet's formation. The regular moons likely originated in their equatorial orbits, concurrently with the planet's formation. The 4 largest moons, Titania, Oberon, Umbriel, and Ariel, arranged by decreasing size, possess densities ranging from 1.4 to 1.7 grams per cubic centimeter. This range is marginally higher than the density of a theoretical object derived from cooling a solar composition combination while eliminating all gaseous components. The remaining object would consist of 60% ice and 40% rock. In contrast to these 4, Miranda, the 5th biggest moon of Uranus, is merely half the size of Ariel or Umbriel. Similar to the smaller moons of Saturn, Miranda possesses a density of 1.2 GCM3, 0.7 Oz in In3, which is marginally below the solar composition value, suggesting an elevated ice-to-rock ratio. Water ice is present in the surface spectra of the 5 principal moons. The moon's lower reflectivities than pure ice suggest that their surfaces are composed of contaminated water ice. The composition of the black region remains unknown. Nevertheless, at wavelengths distinct from water, the surface spectra seem uniformly dark, indicating a neutral grey hue devoid of iron-containing minerals, which would impart a reddish tint. One possibility is carbon, which may have originated from the moon's interiors in the issue, or from the rings of Uranus. This carbon may have emitted methane gas, which dissolved into solid carbon when subjected to charged particles and solar UV radiation. 2 observations suggest that the surfaces of the principal moons are permeable and possess significant insulating properties. The reflectance significantly escalates in opposition when the observer is within 2 degrees of the Sun, as perceived by the planet. These purported opposing surges are typical of loosely arranged particles that obscure one another, except in this specific geometry, where the viewer aligns with the illumination source, allowing direct visibility of the light, reflecting from the interstitial gaps between the particles. Secondly, variations in surface temperatures appear to correlate with solar activity throughout the day, exhibiting negligible delay, attributable to thermal inertia. This phenomenon is typical of porous surfaces that impede the inward transfer of heat. Nearly all knowledge regarding the unique surface features of Uranus's principal moons is derived from Voyager 2, which rapidly traversed the system in hours and captured images solely of their illuminated southern hemispheres. Oberon especially Umbriel, exhibits dense concentrations of substantial impact craters akin to the highlands of Earth's moon and several ancient terrains within the solar system. Umbriel is the most extensively and consistently cratered of the major Uranian moons, indicating minimal tectonic reworking of its surface in the past. Titania and Ariel exhibit significantly fewer huge craters, 5,100 kilometers, 30-60 miles in diameter. However, they possess similar quantities in the other size categories. The extensive craters originated from the solar system's formative period over 4 billion years ago, when substantial planetesimals were still present. In contrast, the smaller craters represent more contemporary occurrences, potentially including impacts from debris ejected from other moons within the Uranian system. Consequently, the surfaces of Titania and Ariel must be more recent than those of Oberon and Umbriel. The discrepancies, which lack a discernible correlation with the moon's proximities to Uranus or their dimensions, remain predominantly unaccounted for. Volcanic deposits identified on the principal moons are predominantly planar, featuring lobate margins and surface undulations, indicative of fluid dynamics. Certain deposits exhibit brightness, while others display darkness. Due to the extremely low temperatures anticipated in the outer solar system, the erupting fluid was likely a water-ammonia amalgam with a melting point significantly lower than that of pure water ice. Variations in brightness may signify disparities in the composition of the erupting fluid or the surface's historical context. The rift-like canyons observed on the principal moons suggest the extension and fracturing of their surfaces. Miranda. Miranda is the innermost and smallest of Uranus's 5 principal moons, exhibiting the most diverse topography. In 1948, Dutch-American astronomer Gerard P. Kuiper identified Miranda in telescopic images of the Uranian system, naming it after a character from William Shakespeare's play The Tempest. Miranda orbits Uranus once every 1.413 days on a nearly circular trajectory at an average distance of 129th of 800 kilometers, 80,654 miles from the planet's center. Somewhat non-spherical, it possesses a mean diameter of around 470 kilometers, 290 miles. The US Voyager 2 spacecraft conducted a more detailed examination of Miranda than any other moon of Uranus, owing to its track during the 1986 flyby of Uranus, which subsequently directed it towards Neptune. Images from Voyager disclose that Miranda's surface is an unusual mosaic of meandering valleys, aligned grooves, fault scarps, and cratered peaks. The primary surface is extensively cratered. However, it is interspersed by 3 lightly cratered areas, designated by astronomers as coronae, which are not geologically associated with the similarly named surface features of Venus. Curved parallel bands encircle the peripheries of these rather square zones, measuring 1 Miranda radius per side. The demarcations where the coronas intersect with the cratered landscape are distinct. The coronae are distinct from any features observed in the solar system. Their origin remains uncertain, whether indicative of a heterogeneous genesis for the Moon, a colossal collision that fragmented it, or a distinctive sequence of internal eruptions. Miranda's canyons are the most magnificent, with some measuring up to 80 kilometers, 50 miles in width, and 15 kilometers, 9 miles in depth. The Moon's volume increase, estimated at 1 to 2%, resulted in crustal rupture, except Miranda, which grew by 6%. Miranda's growth can be elucidated by positing that all the water within its interior was initially in a liquid state, and then froze following the formation of its crust. When subjected to low pressure, the water would have frozen, causing it to expand and then fracture the surface. The existence of liquid water on the Moon's surface at any point in its history appears improbable. The topography variation of Miranda astonished scientists, who assumed the Moon was too diminutive merely one-third the diameter of its far less topographically diverse counterparts, Titania and Oberon. To have experienced the significant tectonic activity necessary to create such different terrain, we must ascertain if this activity originated from external forces, such as one or more catastrophic collisions in the Moon's early history, or intrinsic factors, such as eruptions from its interior caused by historical tidal heating, akin to the phenomena observed on Jupiter's volcanically active moon, Io. Ariel. Ariel is the second closest of Uranus's 5 main moons. In 1851, English astronomer William Lassell found it and named it after characters from Alexander Pope's poem The Rape of the Lock and William Shakespeare's play The Tempest. Ariel orbits Uranus at an average distance of 191,240 kilometers, 118,230 miles, from the planet's center, requiring 2.52 days to complete a single revolution. Ariel, similar to other substantial moons of Uranus, exhibits synchronous rotation with its orbital period, maintaining a constant orientation towards the planet and a consistent forward-facing position in its orbit. The average diameter of the Moon is approximately 1,160 kilometers, 720 miles. The density is approximately 1.67 Gr Symmetrian 3, 0.97 Oz in 3. The US Voyager 2 spacecraft obtained images during its 1986 approach to the Uranian system, showcasing scarps and extensive valley-like landforms traversing Ariel's surface. Substances that may have ascended from the Moon's interior in the past partially occupy several of the latter formations. In certain instances, ice has disseminated from the valleys across extensive plains, like glacier flows on Earth. The characteristics and the scarcity of significant impact craters indicate that Ariel possesses the most youthful surface among Uranus's principal moons. Umbriel. Umbriel is the third closest of Uranus's 5 principal moons, possessing the darkest and most ancient surface. The English astronomer William Lassell discovered Umbriel in 1851. However, it is conceivable that William Herschel, who also found Uranus and its 2 largest moons, observed it almost 50 years prior. Umbriel was designated by John Herschel, son of William Herschel, after a figure in Alexander Pope's poem, The Rape of the Lock. It completes an orbit around Uranus every 4,144 days at an average distance of 265,170 kilometers, 165,270 miles. Umbriel possesses a diameter of 1,170 kilometers, 727 miles, and a density of around 1.4 grams per cubic centimeter, 81 ounces per cubic inch. The photos of Umbriel's surface originated in the United States. The Voyager 2 spacecraft conducted a flyby of the Uranian system in 1986. These indicate that Umbriel is unique among Uranus's major moons due to the absence of evidence for historical tectonic activity, as evidenced by the numerous massive impact craters. The photographs captured by Voyager of the hemisphere reveal a luminous ring termed Wunder, which appears to delineate the floor of a crater with a diameter of 40 kilometers, 25 miles. Titania. Titania is Uranus's biggest moon. William Herschel first observed Titania with a telescope in 1787, having discovered Uranus 6 years earlier. John Herschel, son of William, named Titania after a figure from William Shakespeare's play A Midsummer Night's Dream. Titania orbits at an average distance of 435,840 kilometers, 270,120 miles, from the center of Uranus, rendering it the second outermost of the planet's principal moons. Its orbital period is 8.706 days, identical to its rotational period. It is consequently in synchronous rotation, maintaining the same face oriented toward the planet and the same face directed along its orbit. The diameter measures 1,578 kilometers, 980 miles, and the density is around 1.71 grams per cubic centimeter, 1 ounce per cubic inch. The US occurred only once in 1986. The Voyager 2 spacecraft rapidly traverses the Uranian system and conducts close observations of Titania. Images of the spacecraft reveal a terrain characterized by numerous bright impact craters of up to 50 kilometers, 30 miles, in diameter, with a scarcity of larger craters. There are also trenches and a deep fault line reaching approximately 1,600 kilometer, 1,000 miles. These and other associated characteristics strongly indicate the presence of internal geological processes in the Moon's ancient history. Oberon. Oberon, the outermost of Uranus's 5 principal moons and the second largest, was discovered in 1787 by William Herschel. William's son named it after a character from Shakespeare's play A Midsummer Night's Dream, similar to his choice of Titania. The average distance of Oberon from the center of Uranus is approximately 582,600 kilometers, 362,000 miles, and its orbital period is 13.46 days. Like all of Uranus's substantial moons, Oberon exhibits synchronous rotation with its orbital period, maintaining a consistent hemisphere oriented towards the planet and a fixed hemisphere advancing in its orbit. The Moon possesses a diameter of 1,522 kilometers, 946 miles, and a density of 1.63 grams per cubic centimeter, 0.94 ounces per cubic inch. The US Voyager 2 spacecraft sent photographic photos during its 1986 flyby of the Uranian system, indicating that Oberon's surface is ancient and that certain black material, which upwelled from the Moon's subsurface, seems to have inundated several of the numerous bright craters. The ring system. We initially identified Uranus's rings prior to those of any planet other than Saturn. In 1977, American astronomer James L. Elliott and his colleagues identified the ring system from Earth during a stellar occultation by Uranus, 9 years before the Voyager 2 encounter, when the planet obstructed the light of a star by interposing itself between the star and Earth. They unexpectedly spotted the star temporarily dim 5 times at a significant distance above Uranus's atmosphere, before and after the planet occulted it. 5 slender rings surrounded the planet, as evidenced by the variations in luminosity. Subsequent terrestrial observations disclosed 4 extra rings. Voyager 2 identified a 10th ring and observed evidence of more rings. The 10 rings, designated 6, 5, 4, alpha, beta, eta, gamma, delta, lambda, and epsilon, radiate from Uranus. The intricate terminology arose from identifying new rings in areas inconsistent with the old scheme. The rings are slender and rather opaque. The observed widths result from the integral of the radial distance multiplied by the proportion of starlight obstructed. The observation that the equivalent widths are typically less than the measured widths suggests that the rings are not entirely opaque. The amalgamation of the ring brightness measured in Voyager photos with the corresponding widths from occultations indicates that the ring particles reflect less than 5% of the incident sunlight. Their nearly uniform reflectance spectrum indicates that the particles are predominantly grey in hue. Common soot, primarily composed of carbon, serves as the nearest terrestrial analogue. The origin of the carbon remains uncertain, whether it derives from the darker methane due to particle bombardment or is inherent to the ring particles. The scattering effects of Voyager's radio signal transmitted across the rings to Earth indicate that the rings predominantly comprise massive particles, objects exceeding 140 cm, 4.6 feet, in diameter. When Voyager was positioned on the far side of the rings and directed its camera towards the Sun, the dispersion of sunlight illuminated minute dust particles in the micrometer range. The primary rings contained a minimal quantity of dust. The distribution of numerous tiny particles within the primary rings interstitial spaces, indicates that collisions result in mass loss from the rings. The drag from Uranus's extensive atmosphere and the radiation pressure from sunlight restrict the longevity of dust in orbit around the planet, causing the particles to descend to lower orbits and eventually enter the Uranian atmosphere. The computed orbital lifetimes of 1,000 years require swift and ongoing dust generation. The atmospheric drag of Uranus suggests that its current rings may be ephemeral. If that is the case, the rings did not originate with Uranus, and their provenance and history remain uncertain. Collisions among the densely clustered ring particles would inherently expand the ring's radial breadth. Similar to the rings of Saturn, moons that possess greater mass than the rings can impede this dispersion through shepherding. Voyager 2 discovered that the innermost two moons, Cordelia and Ophelia, orbit opposite sides of the Epsilon ring at the precise radii necessary for shepherding. The moons may be too little to be discernible in the Voyager photos, resulting in the unnoticed shepherds of the other rings. Minor moons may function as reservoirs, providing dust that exits the ring system. William Herschel, an English astronomer, discovered Uranus while studying stars down to the 8th magnitude, approximately 5 times dimmer than those visible to the naked eye. On March 13, 1781, he discovered a peculiar, either nebulous star or possibly a comet, differentiated from the stars by its distinctly visible disk. Within months, the absence of a tail and its sluggish movement determined that the object was a planet rather than a comet or asteroid, traversing a nearly circular orbit well beyond Saturn. Observations of the new planet over the subsequent 65 years uncovered inconsistencies in its orbital motion, indicative of gravitational influences on Uranus, not attributable to any other recognized planet, culminating in the discovery of the more remote Neptune in 1846. Herschel proposed the designation Georgium Sidus, Latin Georgian planet, for his new discovery in honor of his patron, King George III of England, although the French preferred Herschel. The convention of naming planets after deities from Greek and Roman mythology culminated in the designation of Uranus, the progenitor of Saturn, who is, in turn, the progenitor of Jupiter. The initial missions of the twin Voyager 1 and 2 spacecraft were limited to flybys of Jupiter and Saturn. However, the launch schedule of Voyager 2 permitted a trajectory alteration that enabled it to be redirected to Uranus and Neptune for an extended mission, which it successfully executed. On January 24, 1986, Voyager 2 traversed the Uranian system after over 8 years in space. The instruments of Voyager 2 precisely measured the masses and radii of Uranus and its principal moons, identified the planet's magnetic field, assessed its strength and orientation, and evaluated the inner rotation rate of the planet. Over 8,000 images of the Uranian system unveiled for the first time the atmospheric weather patterns of the planet and the surface features of its moons. Besides Voyager's findings of new moons, a ring and dust bands between the rings, it furnished insights into ring structure at sizes unattainable from Earth. Nevertheless, despite these accomplishments, Voyager generated numerous unresolved inquiries that could only be clarified through an additional spacecraft voyage or significant advancements in terrestrial observatory technology. Since 2009, no missions to Uranus have been planned. Neptune. Neptune is the third most massive planet in the solar system and the 8th planet from the Sun. The naked eye cannot perceive it because of its vast distance from Earth. However, through a small telescope, it manifests as a little, faint, blue-green disk. Poseidon, the Greek deity and son of Titan Cronus, Roman god Saturn, is the brother of Zeus, Roman god Jupiter, and the origin of Neptune's name. Utilizing a telescope, scientists identified Neptune as the second planet. The discovery in 1846 exemplified a notable integration of rigorous Newtonian physics, with a reliance on a numerological framework that subsequently was demonstrated to be scientifically invalid. Neptune's orbit is nearly round, resulting in minimal variation in its distance from the Sun throughout its 164-year revolution period. Despite Pluto's mean distance from the Sun being larger than Neptune's, its very eccentric orbit results in Pluto being closer to the Sun than Neptune for approximately 20 years of each revolution. Neptune is over 4 times larger than Earth, but marginally smaller than Uranus, rendering it the smallest in diameter among the 4 big, or Jovian, planets. Nonetheless, it possesses greater mass than Uranus, with a density around 25% superior. Like the other gas giants, Neptune is predominantly composed of hydrogen, helium, water, and many volatile substances, along with rocky material, and lacks a solid surface. Neptune receives less than 50% of the sunlight than Uranus. Nonetheless, geothermal heat emanating from its interior renders Neptune somewhat warmer than Uranus. The heat released may contribute to the storminess of Neptune's atmosphere, which displays the highest wind speeds observed on any planet in the solar system. Before the passage of the Voyager 2 spacecraft in 1989, only 2 of Neptune's 13 moons were identified, and its ring system was not verified until Voyager's exploration. Analogous to Uranus, a solitary spacecraft encounter provided scientists with most of their knowledge regarding Neptune, encompassing its rotation period and the properties of its magnetic field and magnetosphere. Recent advancements in Earth-based observational technology have yielded new insights into the Neptunian system. Neptune's orbital period of 163.72 years indicates that by mid-2010, it will have completed a single revolution around the Sun since its discovery in September 1846. As a result, astronomers anticipate refining their calculations of its orbital dimensions and configuration during the 21st century. The interaction between Voyager 2 and Neptune resulted in a marginal augmentation of the planet's estimated average distance from the Sun, presently calculated at 4,498,250,000 kilometers, 2,195,083,000 miles. The orbital eccentricity of 0.0086 is the second lowest among the planets, surpassed only by Venus's orbit in circularity. Neptune's rotation axis is inclined at 29.6 degrees relative to its orbital plane, exceeding Earth's tilt 23.4 degrees. Like Earth, Neptune's axial tilt results in seasons, and due to the round nature of its orbit, the seasons, and those of its moons, are of almost equal duration, each lasting nearly 41 years. Voyager 2 determined Neptune's rotation period by identifying radio bursts linked to the planet's magnetic field, which exhibited 16.11 hours. We deduced this value to signify the rotation period within the planet's interior, where the magnetic field is generated. The equatorial diameter of Neptune, measured at the 1 bar pressure level, equivalent to Earth's sea level atmospheric pressure, is 49,528 kilometers, 30,575 miles, approximately 3% less than that of Uranus. Neptune's rapid rotation causes the poles to flatten, leading to a polar diameter of 848 kilometers, 527 miles, less than its equatorial diameter. Despite Neptune having a slightly smaller volume than Uranus due to its higher density, 1.64 grams per cubic centimeter compared to around 1.3 for Uranus, Neptune's mass is 18% more. The atmosphere. Like other gas giants, Neptune's outer atmosphere predominantly comprises hydrogen and helium. At the 1 bar pressure level in the atmosphere, these two gases account for approximately 98% of atmospheric molecules. The majority of the residual molecules are composed of methane gas. Hydrogen and helium are almost imperceptible. However, methane exhibits significant absorption of red light. sunlight reflects off Neptune's clouds, resulting in the atmosphere losing much of its red hues and acquiring a bluish tint. Uranus's blue-green hue is attributed to atmospheric methane, whereas Neptune exhibits a more vibrant, brighter blue, perhaps due to an undiscovered atmospheric gas. The temperature of Neptune's atmosphere fluctuates with elevation. Neptune is about 50% farther from the Sun than Uranus, resulting in it receiving less than half the sunlight of Uranus. However, the effective temperatures of these two gas giants are practically identical. Uranus and Neptune reflect and consequently absorb approximately the same fraction of the sunlight that reaches them. Due to processes that are not entirely comprehended, Neptune radiates over twice the energy it absorbs from the Sun. The interior of Neptune produces supplementary energy. In contrast, Uranus has less energy loss from its interior. At the 1-bar reference level, the average temperature of Neptune's atmosphere is approximately 74 K, 326 degrees F, 199 degrees C. Atmospheric temperatures are several degrees higher near the equator and poles compared to mid-latitudes. This signifies that air currents ascend around mid-latitudes and decrease near the equator and poles. This vertical flow can reach significant altitudes inside the atmosphere. A more vertically restricted horizontal wind system is present at the cloud tops. Like other gas giants, Neptune's atmospheric circulation exhibits zonal flow, characterized by winds predominantly moving along lines of constant latitude, east-west, and maintaining relative stability throughout time. Winds on Neptune vary from approximately 100 meters per second, 360 kilometers, 220 miles per hour, in an easterly direction, prograde, aligned with the planet's rotation, at latitude 70 D, to as much as 700 meters per second, 2,520 kilometers, 1,570 miles per hour, in a westerly direction, retrograde, contrary to the planet's rotation, at latitude 20 degrees S. The intense winds and significant internal heat loss may account for the turbulence detected in Neptune's visible atmosphere by Voyager 2. Two prominent black ovals were distinctly observable in Voyager photos of Neptune's southern hemisphere. The largest, referred to as the Great Dark Spot, due to its resemblance in latitude and shape to Jupiter's Great Red Spot, is comparable in size to Earth. We recorded the maximum wind velocities adjacent to this storm system. Telescopes on Earth have monitored Jupiter's Great Red Spot for more than 300 years. Scientists anticipated Neptune's Great Dark Spot would endure for a comparable duration. Scientists were consequently astonished by its absence in photographs of Neptune captured by the Earth-orbiting Hubble Space Telescope in 1991, hardly 2 years post-Voyager visit, as they were by the emergence of a similar black patch in Neptune's northern hemisphere in 1994. The luminous cloud formations shown in the Voyager photos are notably more ephemeral. They could be methane ice clouds formed by vigorous upward movements of methane gas pockets to elevated, colder altitudes in the atmosphere, where the gas condenses into ice crystals. Neptune is the sole big planet exhibiting cloud shadows produced by high-dispersed clouds on a lower, more uniform cloud layer. The primary cloud layer, possibly comprising ice crystals of ammonia or hydrogen sulfide, is 100 kilometers, 30 to 60 miles, above the upper clouds, presumably formed of methane ice crystals. Like other gas giants, Voyager's remote sensing equipment detects deeper cloud layers on Neptune, where the gas composition predominantly comprises sulfur and nitrogen molecules. We anticipate the formation of water ice clouds at depths in Neptune's atmosphere, where the pressure exceeds 100 bars. The magnetic field and magnetosphere. Like other planets in the solar system, Neptune has an internally generated magnetic field, initially identified in 1989 by Voyager 2. Neptune's magnetic field, akin to Earth's, resembles a dipole, similar to a bar magnet, although its polarity is fundamentally opposite to Earth's present field. A magnetic compass on Neptune would indicate south rather than north. Electric currents in Earth's liquid iron core produce its magnetic field, whereas the outer cores of liquid metallic hydrogen in Jupiter and Saturn may similarly generate their magnetic fields. The magnetic fields of Earth, Jupiter, and Saturn are predominantly localized within the planets and aligned within approximately 12 degrees of their rotational axes. In contrast, Uranus and Neptune possess magnetic fields, inclined at almost 59 and 47 degrees from their rotational axes, respectively. Moreover, the fields exhibit a deficiency in internal centering. The offset of Uranus's magnetic field is 31% of the planet's radius, but Neptune's magnetic field, offset by 55%, is situated in an internal region nearer to the cloud tops than the planetary core. Researchers hypothesize that phenomena within the top strata of planetary innards may produce the atypical arrangements of Uranus and Neptune's magnetic fields. The magnetic fields of Neptune and other planets resemble apples, with the stem and opposite end aligned with the magnetic poles. The solar wind, a flow of electrically charged particles from the Sun, alters the planet's regular shape by compressing it on the sunward side and elongating it into a tail directed away from the Sun. Charged particles, primarily protons and electrons, are confined within the magnetic field. The magnetic field of Neptune and its charged particles predominate in the area of space referred to as its magnetosphere. The significant inclination of Neptune's magnetic field consistently directs the entrapped particles in the magnetosphere over the trajectories of the moons and rings. The moons and ring material may absorb numerous particles, significantly depleting the magnetosphere of its charged particle concentration. Neptune's magnetosphere contains a lower density of protons and electrons per unit volume than any other big planet. In proximity to the magnetic poles, charged particles within the magnetosphere can traverse magnetic field lines into the atmosphere. Their collision with gases induces fluorescence in those gases, producing classical, albeit feeble, auroras. Despite having a mean density below 30% of Earth's, Neptune is the most dense among the large planets. This indicates that melting ice and molten rock constitute a greater proportion of Neptune's interior than other giant planets. The distribution of these denser elements and compounds requires more elucidation. Data from Voyager 2 indicate that Neptune is improbable to possess a unique inner core of molten rock components encased by an outer core of liquefied ices composed of methane, ammonia, and water. Based on the layered internal model, Voyager's measured rotation period of 16.11 hours was approximately 1 hour longer than anticipated. Researchers have determined that rather than centrally condensing, the denser chemicals and elements may distribute nearly equally throughout the interior. In this regard, Neptune resembles Uranus more closely than the larger gas giants, Jupiter and Saturn. Neptune may not be hotter at its core than Uranus, even though the planet's interior significantly influences its overall heat budget. Numerous layers in the deep Uranian atmosphere may protect the interior, confining the radiation that more easily dissipates from Neptune within the planet. Photographs of Uranus taken from Earth as it nears an equinox and the Sun progressively illuminates the equatorial regions indicate a more dynamic atmosphere. This suggests that the distinct atmospheric phenomena on Uranus and Neptune are more influenced by solar radiation than the relative quantities of heat emanating from their interiors. Moons and rings of Neptune. Neptune possesses a minimum of 13 moons and 6 identified thin rings. Every particle comprising the rings might be regarded as a little moon in its respective orbit. The 4 moons closest to the planet orbit within the ring system, where some may exert gravitational influence on the ring particles, preventing their dispersion. Before Voyager 2's encounter, Neptune's only identified moons were Triton, visually detected through a telescope in October 1846 by English astronomer William Lassell, shortly after Neptune's discovery, and Nereid, which was identified in telescopic photographs over a century later in 1949 by American astronomer Gerard Kuiper. In 1989, Voyager's observations revealed 6 previously undiscovered moons in Neptune's system. All are situated at less than half of Triton's distance from Neptune and are classified as regular moons, meaning they circle in a prograde direction along roughly circular paths aligned with Neptune's equatorial plane. These moons are likely synchronous rotators, exhibiting identical rotational and orbital periods. Observations from Earth in 2002-03 identified 5 new diminutive moons, each estimated to have a radius of approximately 15 to 30 kilometers, 18 miles. These are irregular, possessing highly eccentric orbits inclined at significant angles to the planet's equator. 3 orbit retrogradely. Their average distances from Neptune range from 15 million to 48 million kilometers, 9 million to 30 million miles, much beyond the orbit of Nereid. Greek mythology links Neptune's moons to Poseidon, the Roman deity Neptune, or water. Of Voyager's 6 discoveries, all but Proteus orbit Neptune in a shorter duration than the planet's rotation period. Consequently, an observer near Neptune's cloud tops would witness these 5 celestial bodies ascending in the west and descending in the east. Voyager closely examined 2 of its findings, Proteus and Larissa, enabling the detection of their size and approximate shape. Both bodies exhibit unusual shapes and display significantly cratered surfaces. We approximate the dimensions of the remaining 4 by analyzing distant photos and their luminosities, presuming they reflect around 7% of the light from Proteus and Larissa. The next 5 moons are far smaller, each possessing a mean radius of under 100 kilometers, 60 miles. The subsequent text provides more detailed profiles of Neptune's 3 largest moons: Triton, Proteus, and Nereid. Triton. The atypical orbital traits of Triton, Neptune's largest moon, indicate that it originated in a different region of the solar system before being captured by Neptune. Triton derives its name from a merman in Greek mythology, recognized as the offspring of the sea deity Poseidon, equivalent to the Roman god Neptune. Triton is distinctive among the solar system's huge moons due to its retrograde orbit, contrary to Neptune's rotation. The average orbital distance is approximately 354,800 kilometers, 220,500 miles, from the Earth. Triton's orbital inclination, exceeding 157 degrees relative to Neptune's equator, is atypical for a sizable moon. The orbits of the other significant moons in the solar system are inclined by less than 5 degrees relative to their planet's equator. Triton completes 1 axial rotation every 5.877 days, which coincides with its orbital period around Neptune. The synchronous rotation causes the moon to consistently present the same face to Neptune while maintaining this orientation throughout its orbit. Triton's seasons, akin to those of Neptune, endure for approximately 41 years, constituting 1/4 of Neptune's orbital period. Triton's orbital inclination, coupled with its axial tilt of 30 degrees about Neptune's orbit, results in the moon's poles periodically orienting toward the sun, akin to the behavior observed in Uranus. Little information was available regarding Triton until 1989, when the United States. The Voyager 2 probe approached within 40,000 kilometers, 24,800 miles of it. As Voyager estimated, Triton has a diameter of approximately 2,706 kilometers, 1,681 miles, nearly equivalent to Earth's moon. Before Voyager, Estimations of Triton's size from Earth relied on an inaccurately elevated mass assessment and a presumption of minimal surface reflection. Triton's mass is now understood to be a mere fraction of the previously recognized amount, and its surface is icy and highly reflective, in contrast to the Moon's dark surface, which is devoid of water and other volatile substances, except for water ice, found in the floors of craters at its poles. The low mass of Triton is probably due to an interior primarily composed of water ice, encasing a denser rocky core. Nonetheless, its average density of 2.06 G Cmin3 E 1.19 Oz E an N3 exceeds that recorded for any satellites of Saturn or Uranus, and is only surpassed among large satellites by the Moon and Jupiter's Io and Europa. Triton exhibits similarities in size, mass and surface composition to the dwarf planet Pluto. Triton's significantly tilted retrograde orbit suggests it is a captured entity, perhaps emerging as an independent, icy planetesimal in the outer solar system, akin to Pluto. At a certain juncture in Neptune's primordial history, Triton's solar orbit may have brought it too near to the colossal planet. The gas drag in Neptune's expansive atmosphere, or a collision with an existing moon of Neptune, decelerated Triton sufficiently to establish it in an elongated, retrograde, and highly inclined orbit. Tidal interactions between Triton and Neptune, cyclical deformations in one celestial body, due to the gravitational pull of the other, would ultimately have altered Triton's orbit around Neptune into a circular trajectory. Triton's capture and orbital circularization would have significantly disturbed any pre-existing moon system, formed with Neptune from a disk of protoplanetary material. We have not dismissed the notion that Nereid is a captured object. Nonetheless, this procedure may have resulted in Nereid's eccentric orbit. The molten Triton would have either absorbed the moons in closer orbit to Neptune, expelled them from the Neptunian system, or impacted Neptune directly. Even the moons in closer orbit to Neptune would have undergone considerable disruption. The current orbits of Naiad and Proteus likely diverge significantly from their original trajectories, suggesting that these moons may merely be remnants of the primordial bodies that coalesced with Neptune. The subsequent bombardment by debris orbiting Neptune and meteoroids from interplanetary space may have further modified their sizes, shapes, and orbits. Methane and nitrogen ice cover Triton's visible surface. Spectroscopic investigations from Earth indicate the presence of trace quantities of carbon monoxide and carbon dioxide ice. Voyager recorded the surface temperature as 38 K, equivalent to 390 degrees in AD 235 degrees. Nevertheless, sufficient frozen nitrogen sublimes to generate a tenuous atmosphere with a pressure of less than 0.02 bar at the surface. During the Voyager flyby, a polar ice cap, apparently consisting of nitrogen ice deposited the previous winter, encompassed most of Triton's southern hemisphere. At that time, Triton was approximately halfway through its 41-year southern spring. Equatorward of the polar cap, the terrain resembled a cantaloupe rind, characterized by dimples interspersed with a network of fractures. Numerous darker streaks within the polar cap region indicate the presence of surface winds. At least two of the streaks, perhaps many, originate from active geyser-like plumes observed during the Voyager 2 flyby. Ventilation in the superjacent ice permits the release of nitrogen gas, transporting suspended dust particles to altitudes of around 8 kilometers, 5 miles, from whence they disperse downwind up to 150 kilometers, 90 miles. Although we still need to complete our understanding of the energy sources and mechanisms propelling these plumes, their inclination towards latitudes irradiated vertically by the sun suggests that incident sunlight plays a crucial role. On the Neptune-facing side of Triton, near the equator, there are at least two, and perhaps numerous, frozen lake-like formations with terraced peripheries. The terracing results from numerous melting epochs, with each subsequent melt affecting a reduced ice area. Certain terrace cliffs ascend beyond 1 kilometer, 0.6 miles, in height. Despite Triton's low surface temperature, nitrogen or methane ice needs more strength to hold constructions of that height without succumbing to slumping. Despite the absence of concrete evidence in Triton's spectra, scientists hypothesize that water ice is the foundational element in these formations, which exhibit a more rock-like consistency at low temperatures. A small layer of nitrogen or methane ice may obscure water ice's spectral signature. The transition from capture to circular orbit may have exceeded 1 billion years, during which the significant tidal deformations endured by Triton likely resulted in the melting of its whole interior. The molten mass would have experienced differentiation, causing denser materials to descend into the core, while more volatile substances ascended to the surface. Scientists argue that Triton's surface cooled more rapidly than its innards, forming a dense outer layer, predominantly of water ice. Proteus is Neptune's second biggest moon, named for the prophetic, shape-shifting elder of the sea in Greek mythology. It was among the moons identified by Voyager 2 in 1989. Proteus has a mean radius of around 208 kilometers, 129 miles, making it slightly larger than Nereid, which has a mean radius of about 170 kilometers, 106 miles. Nevertheless, due to Proteus's proximity to Neptune, terrestrial scientists could not discern it amidst the planet's luminosity. Nereid is the third largest moon identified in Neptune. In Greek mythology, it is named after the many daughters of the sea deity Nereus, known as Nereids. Nereid possesses a diameter of around 340 kilometers, 210 miles, with a period exceeding 360 days and an inclination greater than 7 degrees relative to the planet's equator. Nereid orbits Neptune with the most eccentric trajectory of any known moon. Its average distance from Neptune is 5,530,400 kilometers, 3,425,900 miles, approximately 15 times greater than the nearest known moon, Triton. Nereid is exceptionally dim, rendering studies with even the most powerful Earth-based telescopes somewhat challenging. Consequently, the available information is limited. However, the US provides reflectivity data. The Voyager 2 space probe in 1989 indicated a surface composition of ice and silicates. The concept posits that Neptune's gravitational influence ensnared Triton, a sibling of Nereid, whose protracted settling-in period, lasting 1 billion years, significantly disturbed Neptune's primordial moon system. Nereid may be a captured body originating in a different solar system region. Voyager did not detect Nereid at close proximity. However, data from the probe suggests that it possesses a nearly spherical morphology. Voyager saw no significant fluctuations in brightness during Nereid's rotation. The spacecraft could not ascertain a rotation period. Nonetheless, the moon's elliptical orbit renders synchronous rotation improbable, meaning its rotation and orbital periods are unequal. Evidence of one or more rings around Neptune emerged in the mid-1980s, when stellar occultation investigations from Earth sometimes revealed a transient decrease in a star's brightness immediately before or after the planet obscured it. Scientists determined that the rings detected do not fully encircle Neptune. Rather, they manifest as partial rings or ring arcs, as evidenced by the reported dips in certain studies, which were never symmetrical on both sides of the planet. Images from Voyager 2, however, disclosed a system of 6 rings, each completely around Neptune. Voyager 2 revealed the alleged arcs as luminous areas in the outermost ring, atoms, characterized by a notably high density of ring particles. While rings also surround the other 3 gas giants, none exhibit the remarkable clumpiness characteristic of atoms. The 5 further recognize rings of Neptune, Gal, Le Verrier, Lasselle, Arago, and Galatea, arranged by ascending distance from the planet, do not have the density, non-uniformity characteristic of atoms. Leverrier, with a radial diameter of approximately 110 kilometers, 70 miles, closely matches the non-arc areas of atoms. Similar to the relationship between the moon Galatea and the ring atoms, the moon Despina orbits Neptune within the ring Leverrier. Each moon may gravitationally resist particles at the inner boundary of its corresponding ring, functioning as a shepherd moon to prevent the inward dispersion of ring material. Gale, the innermost ring, is considerably wider and dimmer than both Adams and Leverrier, probably because no proximate moon is capable of providing a substantial shepherding influence. A subtle plateau of ring material, referred to as Lassell, extends outward from Leverrier to around the midpoint of Adams. Arago is the tiny, somewhat luminous area around the periphery of Lassell. Galatea often denotes a tenuous ring of material that spans the moon's orbit. The scattering effects on Voyager's radio signal did not identify Neptune's rings, indicating a near-complete absence of particles of centimeter size or larger. Sunlight illuminating the rings in Voyager photos indicated that they were predominantly dust-sized particles, which scatter light more efficiently forward than back toward the Sun and Earth. The chemical composition remains unknown. However, akin to the rings of Uranus, the surfaces of Neptune's ring particles may consist of radiation-altered methane ices, and possibly the particles themselves. We can extrapolate the presumed youthfulness of Adams's ring arcs and the accompanying arguments to Neptune's rings. The current rings are slender, and researchers have struggled to elucidate how the trajectories of the observed moons can adequately restrict the inherent radial dispersion of the rings. This has prompted speculation that Neptune's current rings may be far younger than the planet, possibly less than 1 million years old. The current ring system may significantly differ from those that existed 1 million years prior. The forthcoming spacecraft visiting Neptune's rings may encounter a more advanced system than that which Voyager 2 captured in 1989. The only large planet that requires a telescope for observation is Neptune. With an apparent magnitude of 7.8, it is roughly 1/5 as luminous as the dimmest stars observable without optical help. Consequently, sightings of Neptune occurred after the advent of telescopes. Galileo began using a telescope to observe the cosmos in 1609. On December 28, 1612, he produced his initial sketches, indicating that he observed Neptune near Jupiter, but still needed to identify it as a planet. Before the discovery of Uranus by the English astronomer William Herschel in 1781, scientists and philosophers believed that the solar system had only 6 planets, Earth and the 5 planets observable in the sky since antiquity. The discovery of a 7th planet prompted astronomers and others to hypothesize the presence of more planetary entities. The mathematical phenomenon known as Bode's law provided further motivation. Some astronomers were amazed by how well Bode's rule explained the distances between Ceres and Uranus. They came up with the name Ophion for the solid planet that the law said must exist beyond Uranus at 38.8 AU. Besides this scientifically baseless claim, investigations of Uranus yielded evidence for the existence of another planet. Newton's equations of motion and the gravitational influences of the Sun and other planets failed to forecast Uranus's trajectory. Moreover, more than 20 documented pre-discovery sightings of Uranus, originating from 1690, exhibited inconsistencies with the computed locations of Uranus for each observation. The gravitational pull of an undiscovered planet is affecting the orbit of Uranus. In 1843, British mathematician John Couch Adams commenced an earnest investigation to ascertain the whereabouts of a more remote planet that would explain Uranus's anomalous movements. Adams conveyed his findings to the Astronomer Royal, George B. Airy, at the Greenwich Observatory, but they needed more precision to initiate a sufficiently focused search for the new planet. In 1845, Urbain Jean-Joseph Leverrier of France, oblivious to Adams's endeavours in Britain, initiated a comparable investigation. By mid-1846, English astronomer John Herschel, son of William Herschel, articulated his belief that the ongoing mathematical investigations could potentially result in finding a new planet. Convinced by Herschel's reasoning, Airy recommended a search based on Adams's estimates to James Challis at the Cambridge Observatory. Challis initiated a methodical investigation of an extensive region of the sky adjacent to Adams's anticipated position. Challis's absence of comprehensive maps of the faint stars in the anticipated region of the new planet rendered the search protracted and laborious. He would create charts of the stars he viewed and compare them with the same spot several nights later to ascertain if any had shifted. Leverrier faced challenges in persuading astronomers in his nation that conducting a telescopic survey of the region he identified for the new planet was worthwhile. On September 23, 1846, he conveyed his findings to the German astronomer Johann Gottfried Galle at the Berlin Observatory. Galle and his helper Heinrich Louis d'Arrest utilized meticulously crafted star maps to facilitate the search for new asteroids. Galle and d'Arrest recognized Neptune as an unknown celestial body that evening and confirmed its movement about the background stars the following night. While Galle and d'Arrest were the initial observers of Neptune in the night sky, the credit for its discovery probably resides with Leverrier, due to his calculations regarding Neptune's trajectory. Initially, the French endeavored to designate Leverrier as the exclusive discoverer of the new planet and proposed that it be named in his honor. The acknowledged contribution of Adams and the widespread reluctance to name a major planet after a contemporary individual negatively impacted the proposal's acceptance beyond France. Adams and Leverrier ultimately garnered recognition for the discovery of Neptune, although it now appears that Adams's role was less significant than previously assumed. It is fitting that the conventional practice of naming planets after figures from ancient mythology ultimately triumphed. The discovery of Neptune conclusively refuted Bode's law. The discovery revealed that Neptune's distance from the Sun was 30.1 AU, considerably less than the expected 38.8 AU. The inconsistency and lack of scientific rationale for the law's function undermined its credibility. The vast distance of Neptune from Earth and the Sun significantly hindered observations of the planet from Earth before Voyager 2's flyby. The average orbital radius of 30.1 AU indicates that the sunlight reaching its moons and upper atmosphere is just 0.1% as intense as Earth's. Before the Voyager mission, telescopic observations of Neptune through the entirety of Earth's atmosphere could not discern features smaller than 1/10 of Neptune's diameter, even under optimal viewing conditions. Most observations focused on ascertaining Neptune's dimensions, mass, density, and orbital characteristics, and investigating its moons. In the early 21st century, specialized interferometric techniques have consistently enhanced the spatial resolution of distant objects by factors of 10 to 100 compared to previous surface-based observations. Astronomers intermittently documented visible features in Neptune's atmosphere, but it was in the 1980s that they employed high-resolution infrared charge-coupled device (CCD) cameras to conduct these observations consistently, enabling them to ascertain an approximate rotation period for Neptune. Spectroscopic measurements conducted from Earth indicated the existence of hydrogen and methane in the planet's atmosphere. Compared with the other gas giants, we anticipated the existence of helium. Infrared and optical analyses indicated that Neptune possesses an interior heat source. By the mid-1990s, the fully operational Hubble Space Telescope, HST, facilitated the acquisition of photos and data regarding Neptune, circumventing the filtering and distorting influences of Earth's atmosphere. The Spitzer Space Telescope, orbiting in infrared, successfully captured images of Neptune with a resolution significantly superior to those obtainable from Earth's surface in the 1980s. Astronomers have devised methods to mitigate the impact of air distortion in Earth-based observations. The most effective of them, termed adaptive optics, continuously analyzes data from infrared star pictures and promptly adjusts the telescope mirror's shape to rectify distortion. As a result, huge Earth-based telescopes consistently attain resolutions superior to the HSTs. Images of Neptune captured using adaptive optics facilitate investigations of this remote planet at resolutions nearing those achieved during the Voyager 2 mission. Voyager 2 is the sole spacecraft to have interacted with the Neptunian system. Launched in 1977, Voyager 2 and its counterpart Voyager 1 initially planned to explore only Jupiter and Saturn. However, the timing of Voyager 2's launch allowed for a trajectory adjustment, utilizing a gravity assist from Saturn, enabling extended missions to Uranus and Neptune. Voyager 2 traversed Neptune and its moons on August 24-25, 1989, conducting nearly continuous system observations from June to October. The measurement of the planet's radius and internal rotation rate, along with the detection of its magnetic field, revealed that it is significantly inclined and displaces the planet's rotational axis. We have verified the presence of rings on Neptune and discovered 6 new moons. Voyager's photographs of Neptune revealed the most intense atmospheric winds in the solar system and numerous large-scale storms, one of which is comparable in size to Earth. As Neptune was Voyager 2's final planetary destination, mission scientists took the risk of positioning the spacecraft closer to it than to any other planet throughout the trip. Voyager traveled approximately 5,000 kilometers, 3,100 miles, over Neptune's northern pole. Several hours later, it approached within 40,000 kilometers, 24,800 miles of Triton, enabling the acquisition of high-resolution photos of the Moon's diverse surface and accurate measurements of its radius and surface temperature. As of 2009, there are no proposed missions to Neptune, Pluto, the Kuiper Belt, and beyond. Neptune is the outermost planet in the solar system. Beyond Neptune lies not vacant space, but many peculiar ice-bound celestial bodies, including the Kuiper Belt and its most prominent constituent, the dwarf planet Pluto. Historically, scientists regarded Pluto as the most distant and tiniest planet. In 1930, scientists regarded Pluto as the most recently identified planet. In August 2006, the scientific community mandated the International Astronomical Union to exclude Pluto from the planetary roster and designate it as a dwarf planet. The alteration signifies astronomers' acknowledgement that Pluto is a substantial constituent of the Kuiper Belt, a conglomeration of icy and rocky remnants from the solar system's inception, orbiting the Sun beyond Neptune's trajectory. Pluto is not visible to the human eye in the night sky. Nonetheless, its largest moon, Charon, is sufficiently comparable to the dwarf planet, leading to the prevalent designation of the two entities as a double system. Pluto, named after the Roman deity of the underworld, with Hades as its Greek counterpart, lies at such a distance that sunlight, traveling at approximately 300,000 kilometers, 186,000 miles per second, takes over 5 hours to reach. A person on Pluto's surface would perceive the Sun as an exceptionally luminous star in the dark sky, delivering around 1,600 of the sunlight that reaches Earth. Pluto's surface temperature is so low that ordinary gases like nitrogen and carbon monoxide exist as ice. Due to Pluto's distance and diminutive size, the most advanced telescopes on Earth and in orbit have been unable to discern much detail on its surface. determining fundamental data such as Pluto's radius and mass has been difficult. The discovery of Charon in the late 1970s has significantly contributed to our understanding of Pluto. Despite the absence of previous spacecraft visits to Pluto, the US probe New Horizons launched from Earth in 2006 and plans to reach the Pluto-Charon system in July 2015. Only detailed robotic observations can address numerous critical inquiries regarding Pluto and its surroundings. Pluto's average distance from the Sun, around 5.9 billion kilometers, 3.7 billion miles, or 39.5 AU, results in an orbit exceeding Neptune's outermost planet. Compared to the other planets, Pluto's orbit exhibits several unique characteristics. The orbit of Pluto is more extended or eccentric than any other planetary orbit, and it exhibits a greater inclination, 17.1 again, to the ecliptic, the plane of Earth's orbit, where most planetary orbits lie. Pluto's orbit around the Sun ranges from 29.7 AU at perihelion to 49.5 AU at aphelion. Due to Neptune's almost circular orbit of 30.1 AU, Pluto is closer to the Sun for a brief period during each cycle than Neptune. However, the two celestial bodies will never intersect, because Pluto is in a stabilizing 3.2 resonance with Neptune. Specifically, it completes 2 cycles around the Sun in the same duration. Neptune completes 3. This gravitational contact influences their orbits, preventing them from approaching closer than 17 AU. Pluto last attained perihelion in 1989. For approximately a decade preceding and following that event, Neptune was further from the Sun than Pluto. Observations of Earth have determined Pluto's rotation period, or sidereal day, to be 6.3873 Earth days. Among the celestial bodies, only Mercury, with a rotation period of approximately 59 days, and Venus, with a rotation period of 243 days, exhibit slower rotation. Pluto tilts its rotational axis at an angle of 120 degrees to the perpendicular of its orbital plane, positioning its north pole 30 degrees below this plane. On the other hand, Earth's north polar axis tilts at a perpendicular angle of 23.5 degrees, placing it above its orbital plane. Pluto rotates almost horizontally retrogradely. An observer on its surface would witness the Sun rising in the west and setting in the east. In comparison to the planets, Pluto has abnormal physical features. Pluto's radius is less than 50% of Mercury's. It is approximately 2/3 the size of Earth's moon. Compared to the outer planets, such as the massive Jupiter, Saturn, Uranus, and Neptune, Pluto's radius is remarkably small. By integrating these attributes with our knowledge of its density and composition, Pluto appears to exhibit greater resemblance to the substantial ice moons of the outer planets than to any of the planets themselves. Neptune's moon, Triton, is its nearest counterpart, indicating a potentially analogous origin for both celestial bodies. The atmosphere. Scientists gained confidence in the presence of an atmosphere when they detected methane ice on Pluto's surface in the 1970s, but they delayed direct observation until the following decade. In 1988, Earth witnessed Pluto occulting a star, resulting in the discovery of its atmosphere. The star's luminosity progressively diminished before its obscuration by Pluto, indicating the existence of a tenuous, significantly expanded atmosphere. Minor temperature fluctuations significantly influence Pluto's atmosphere, composed of vapors in equilibrium with their ices, and can substantially alter its gas volume. In the years near Pluto's perihelion in 1989, when its temperature was marginally warmer than usual, a greater volume of its frozen gases sublimated, resulting in an atmosphere at or near its maximum density, providing an advantageous opportunity for study. Astronomers estimate the surface pressure between a few and several tens of microbars. Pluto's atmosphere may be undetectable at aphelion because of minimal solar exposure. Observations conducted during occultations do not yield direct data regarding atmospheric composition. However, they facilitate the calculation of the ratio of mean molecular weight to temperature. Based on acceptable assumptions on atmospheric temperature, scientists have determined that the mean molecular weight of each particle, specifically each atom or molecule, in Pluto's atmosphere is around 25 atomic mass units. This indicates that substantial quantities of gases denser than methane, with a molecular weight of 16, must also exist. Identifying nitrogen ice on the surface, which exhibits greater volatility than methane ice, suggests that molecular nitrogen is the predominant component with a molecular weight of 28. Nitrogen is the primary component of the atmospheres of Triton, Titan, and Earth. While continuous Earth-based observations will enhance understanding of Pluto's atmosphere and other characteristics, significant new revelations would necessitate a direct encounter with a mission. Researchers examined the United States. The New Horizons spacecraft mission, initiated in 2006, aims to explore Pluto, Charon, and the outer solar system to gather essential data. The mission design anticipated a 9-year voyage to the Pluto-Charon system, succeeded by a 150-day flyby to investigate the surfaces, atmospheres, innards, and spatial environment of the two celestial planets. Observations of Pluto indicate that its hue is somewhat reddish, yet somewhat less so than that of Mars or Jupiter's moon Io. Therefore, the observed brightness variations resulting from its rotation confirm that Pluto's surface cannot consist solely of pure ice. Its mean reflectivity, or albedo, is 0.55, indicating it reflects 55% of the incident light, in contrast to 0.1 for the Moon and 0.8 for Triton. Initial rudimentary infrared spectroscopic measurements indicate Pluto's atypically luminous southern polar area. Scientists consider the variance in Pluto's surface remarkable since, aside from Saturn's enigmatic moon, Iapetus, all other frozen worlds in the outer solar system display significantly more uniform surfaces. Brightness maps made from observations with the Hubble Space Telescope, while it was orbiting around the Earth, show some of this diversity. However, only visiting spacecraft can provide the spatial resolution to connect brightness with surface composition or topography. Pluto-Charon eclipses have enabled astronomers to ascertain the masses and radii of both celestial bodies. The predicted densities range from 1.92 to 2.06 GC-CM3, 1.11 to 1.19 Oz-3 for Pluto, and from 1.51 to 181 GCM3, 0.87 to 1.05 Oz-3 for Charon. These numbers indicate that both entities consist of a substantial proportion of materials, including silicate rock and organic molecules, denser than water ice, with a density of 1 G 0.50 Oz-3. It is conventional to presume that Pluto, akin to the frigid moons of Jupiter and Saturn, possesses an inner rocky core encased in a substantial mantle of water ice. We anticipate that the frozen nitrogen, carbon monoxide, and methane detected on its surface will create a comparatively thin layer similar to the water on Earth's surface. Nonetheless, such a model necessitates validation through spacecraft observations. The measurement of Pluto's surface temperature has proven to be exceedingly challenging. The Earth-orbiting infrared astronomical satellite took measurements in 1983 and found temperatures between 45 and 58 K, 379 to 355 degrees, 228 to 215 degrees Celsius. Surface measurements at millimeter wavelengths show temperatures in a slightly lower range of 35 to 50 K, 397 to 370 degrees, 238 to 223 degrees Celsius. The temperature must indeed fluctuate over the surface, contingent upon the reflectance at specific locations and the angle of the noon sun. We anticipate a threefold reduction in solar energy incidence on Pluto as it moves from perihelion to aphelion. Moons of Pluto. Pluto has 3 identified moons, Charon, the biggest moon, is almost half Pluto's diameter. The two bodies orbit a common center of mass at approximately 19,640 km, 12,200 miles, equivalent to nearly 8 diameters of Pluto. In comparison, Earth's moon is slightly larger than 1/4 of Earth's size, and is roughly 30 Earth diameters away from it. Charon's orbital period precisely matches Pluto's rotational cycle. Thus, Charon is in a synchronous orbit around Pluto. Consequently, Charon is observable from just one hemisphere of Pluto. Like communication satellites in geostationary orbits around Earth, Charon maintains a fixed position above a specific place on Pluto's surface, never rising or setting. Moreover, like most moons in the solar system, Charon exhibits synchronous rotation, meaning it consistently shows the same face as Pluto. Charon possesses a lower albedo, about 0.35, than Pluto, and exhibits a more neutral coloration. The spectrum indicates the existence of water ice, which is the predominant surface component. Unlike its larger counterpart, the spectrum does not indicate solid methane. Current investigations have failed to identify ices composed of nitrogen or carbon monoxide. Nevertheless, the lack of methane, which is less volatile, suggests their probable absence. The density of Charon suggests that the moon comprises components including silicates and organic compounds that are denser than water ice. Charon has a more conjectural mineral arrangement than Pluto. Researchers have utilized Charon's presence to uncover various attributes of Pluto that would remain unknown, namely its mass and dimensions. The remarkable coincidence that began 5 years of mutual eclipse events between Charon and Pluto in 1985, just 7 years after Charon's discovery, provided a significant portion of this information. During this period, Pluto transited and occulted the Moon every 6.4 days, as observed from Earth. These events transpire as Earth traverses Charon's orbital plane surrounding Pluto, occurring twice within Pluto's 248-year solar orbit. Meticulous observations of these occurrences facilitated more accurate calculations of the radii of Pluto and Charon and the masses of both celestial bodies. Furthermore, seeing the variations in the total luminosity of the two entities as they obscured one another enabled astronomers to ascertain their respective albedos and to generate maps illustrating brightness disparities throughout their surfaces. If their surface reflectance is similar to Charon's, Pluto's other two moons, Hydra and Nix, provisionally named S2005P1 and S2005P2, respectively upon discovery, are significantly smaller than Charon, with diameters of approximately 60 and 50 kilometers, 37 and 31 miles, respectively. They orbit Pluto outside Charon's trajectory, in almost circular paths, similar to Charon, and within the same orbital plane as Charon. Preliminary observations indicate that Hydra has an orbital radius of approximately 64,700 km, 40,200 miles, while Nix has an orbital radius of about 49,400 km, 30,700 miles. Charon completes around 12 orbits for every 2 orbits of Hydra, resulting in a 6.1 ratio of their orbital periods, whereas Nix completes nearly 3 orbits, yielding a 4.1 ratio. Hence, the orbital periods of Hydra and Nix are in a 3.2 ratio. The relationship between the orbital periods displays small integer values. This indicates that the minor moons maintain stable dynamic resonances with Charon and one another. This indicates that all 3 celestial entities consistently traverse one another and engage gravitationally, ensuring the regularity of these interactions. Pluto and its satellites were discovered. Pluto's discovery established it as the 3rd planet identified, after Uranus and Neptune, among the 6 planets seen to the naked eye since antiquity. Commencing in the late 19th century, astronomers hypothesized the presence of a 9th planet due to observable anomalies in Uranus's orbital motion, indicating that a more remote world was exerting gravitational influence upon it. Astronomers subsequently recognized that these perturbations were illusory. The gravitational influence of Pluto's diminutive mass was insufficient to account for the alleged disturbances. Consequently, the discovery of Pluto resulted from meticulous observations rather than precise predictions regarding the presence of a theoretical planet. The Lowell Observatory in Flagstaff, Arizona, actively facilitated the hunt for the anticipated planet in the early 20th century. Percival Lowell, the originator of the observatory and an American astronomer renowned for his extensively reported canal observations on Mars, commenced the hunt. Following two unsuccessful endeavors to locate the planet before Lowell died in 1916, an astronomical camera designed explicitly for this task and capable of capturing light from an extensive sky area was deployed in 1929, and a young amateur astronomer, Clyde Tombaugh, was employed to conduct the search. On February 18, 1930, less than 1 year after commencing his research, Tombaugh discovered Pluto in Gemini's constellation. The item manifested as a faint 15th magnitude star that gradually altered its location relative to the stationary background stars while it traversed its 248-year orbit around the Sun. Notwithstanding Lowell and other astronomers' forecasts that the unidentified planet would be far larger and more luminous than the celestial body Tombaugh identified, Pluto's recognition as the anticipated ninth planet was rapid. The initial letters of Pluto, plus the initials of Percival Lowell, constitute its emblem. Photographic representations of Pluto in the United States. The Naval Observatory Station in Flagstaff, situated less than 6 kilometers, 3.7 miles, from Pluto's discovery site, facilitated the discovery of Charon in 1978. James W. Christie and Robert S. Harrington captured these photos to achieve more precise estimations of Pluto's orbit. The newly launched satellite is named after the Greek mythological boatman who transports deceased souls to Hades' domain in the underworld. Before the discovery of Charon, scientists erroneously saw Pluto as larger and more massive than it truly is, yet they could not ascertain either measurement firsthand. The initial discovery photographs depict Charon as an indistinct protrusion on Pluto's surface, highlighting the observational challenges posed by the proximity of the two celestial bodies, their considerable distance from Earth, and the atmospheric distortions caused by Earth. After the 20th century, astronomers first distinguished Pluto and Charon as independent entities with the advent of the Hubble Space Telescope, and Earth-based devices utilizing adaptive optics to counteract air turbulence. A group of 9 astronomers in the United States identified Pluto's 2 minor moons, Hydra and Nix, in 2005, from photos captured by the Hubble Space Telescope, during a coordinated search for objects orbiting Pluto with diameters as small as 25 kilometers, 16 miles. To verify the orbits, scientists examined Hubble photos of Pluto and Charon taken in 2002 for surface mapping research, and saw subtle yet definitive signs of 2 objects traversing the orbital trajectories computed from the 2005 data. The Kuiper Belt. Pluto is a member of a planar array of ice minor celestial planets that orbit the Sun beyond Neptune's trajectory. Designated after the Dutch-American astronomer Gerard P. Kuiper, it consists of hundreds of millions of objects, believed to be remnants from the outer planet's formation, whose orbits are situated near the solar system's plane. It is believed that most reported short-period comets, particularly those with orbits about the Sun lasting less than 20 years, as well as the cold Centaur objects around the giant planets, originate from this system. Certain centaurs may signify the evolution from Kuiper Belt objects to short-period comets. In the 1990s, the development of advanced telescopes and sensitive light detectors led to the discovery of the Kuiper Belt, defying long-standing assumptions. In 1943, Irish astronomer Kenneth E. Edgeworth posited that Pluto's present distance did not constrain the distribution of the solar system's minor bodies. In 1951, Kuiper established a more compelling argument. He used an analysis of the mass distribution of bodies necessary for planet formation at the start of the solar system to show that there is more than one comet, nucleus, or small icy bodies beyond Neptune. In the previous year, Dutch astronomer Jan Oort posited the presence of a remote spherical reservoir of frozen bodies, today referred to as the Oort Cloud, which perpetually replenishes comets. This remote source sufficiently explained the genesis of long-period comets, with periods exceeding 200 years. Kuiper observed that comets, with short orbital periods, 20 years or fewer, travel in the same direction as all the planets around the Sun, near the plane of. The solar system requires a more proximate, condensed supply. American astronomer Martin Duncan and colleagues reiterated this elucidation in 1988, which constituted the most compelling evidence for the presence of the Kuiper Belt until its direct observation. In 1992, American astronomer David Jewitt and graduate student Jane Liu identified the inaugural Kuiper Belt object, KBO. Designated as 1992 QB1, the object's diameter is around 250 km, 125-155 miles, as inferred from its luminosity. It traverses a roughly circular orbit within the plane of the planetary system at an approximate distance of 44 AU from the Sun. This is beyond Pluto's orbit, which has an average radius of 39.5 AU. Astronomers identified around 800 Kuiper Belt objects within 12 years, following the discovery of QB1 in 1992. Most are located 30 to 50 AU from the Sun and must possess a diameter over 100 kilometers to be observable. According to brightness estimates, the dimensions of the bigger known Kuiper Belt objects, KBOs, are comparable to or beyond the diameter of Pluto's biggest moon, Charon, which measures 1,250 km, 780 miles. One KBO, designated Eris, seems to possess a diameter twice that of Pluto. We refer to them as trans-Neptunian objects because they are located beyond Neptune's orbit, with a mean radius of 30.1 AU. We can identify two primary categories of KBOs: those in nearly circular stable orbits, and those in very eccentric, elongated orbits, with significant inclination to the solar system's plane. Many of these objects endure solely due to their stabilizing 3.2 resonance with Neptune, meaning they complete 2 orbits around the Sun for every 3 orbits completed by Neptune. Pluto possesses an eccentric, inclined orbit and maintains a 3.2 resonance with Neptune. Pluto is typically considered a substantial Kuiper Belt object, KBO, due to its orbital attributes, composition of ice and rock, and relatively modest size compared to the planets, smaller than Earth's moon. We have designated the other KBOs with 3.2 resonances as Plutinos, little Plutos, to acknowledge this relationship. A minor fraction of KBOs constitutes a third category: those with extended inclined orbits that do not exhibit resonance with Neptune. Their erratic orbits can displace them onto trajectories distant from the Sun or into the inner solar system, potentially converting them into short-period comets. An extrapolation of KBO finding statistics indicates that over 100,000 objects exceeding 100 kilometers in diameter, and likely millions of smaller objects down to 1 kilometers, 0.6 miles, are present between 30 and 50 AU. The population may expand outward, but the extent of its reach and whether it attains the innermost edge of the Oort Cloud remains uncertain. Astronomers typically see the Kuiper Belt as the outer remains of the extensive protoplanetary disk that existed approximately 4.5 billion years ago, which did not succeed in forming substantial planets beyond Neptune's current orbit. This is the genesis of Pluto and its satellites. People commonly believed that Pluto was a former moon of Neptune that had mysteriously escaped its orbit before the discovery of Charon. This concept received endorsement because of the evident resemblance in the proportions of Pluto and Triton and the close alignment of Triton's orbital period, 5.9 days, with Pluto's rotation period, 6.4 days. Researchers proposed that approximate interaction between these two celestial entities, as moons resulted in Pluto's expulsion from the Neptunian system and Triton's present retrograde orbit. Astronomers struggled to ascertain the probability of all these events transpiring, and Charon's discovery offered evidence that contradicted the notion. Given that Pluto's revised mass is merely half that of Triton, Pluto could not have induced the reversal of Triton's orbit. A somewhat big moon around Pluto renders the escape hypothesis improbable. Contemporary theories support that Pluto and Charon originated as two distinct entities within the solar nebula, the gaseous cloud from which the solar system coalesced. A similar mechanism explains the absence of methane on Charon and the relatively high densities of both Pluto and Charon. This is similar to the Moon's high-temperature formation, which appears deficient in volatile elements compared to Earth. Astronomers contend that Pluto's two diminutive moons are also remnants of the collision that produced the current Charon. The other idea is that the two small bodies came from different places in the outer solar system and were then pulled together by the gravitational pull of the Pluto-Charon system. This seems unlikely, given that they are currently seen to be in circular coplanar orbits and experiencing multiple dynamic resonances with Charon. These conditions suggest that the debris ring resulting from the collision coalesced into all three moons, and maybe into yet-to-be-discovered moons. This collision hypothesis suggests that several ice worlds of similar size to these two populated the outer solar nebula when the Pluto-Charon system originated some 4.6 billion years ago. Smaller entities, now identified as comet nuclei, have accumulated their mass. The colossal planets assimilated most of these ice planetesimals into their cores during their formation. Numerous celestial bodies, including the peripheral region of Pluto's orbit, have persisted as the unaggregated remnants constituting the Kuiper Belt. Astronomers determined that Pluto, Charon, Chiron, Neptune's moon Triton, and various other ice moons of the outer planets probably formed as Kuiper Belt objects, KBOs, following direct observations of over 1,000 KBOs beginning in the early 1990s. The Oort Cloud. Situated beyond the Kuiper Belt, the Oort Cloud is an extensive, approximately spherical accumulation of frozen tiny planets that circle the Sun at distances generally exceeding 1,000 times that of Neptune's orbit. The outermost recognized giant planet. The Oort Cloud, named after Jan Oort, who confirmed its existence, consists of particles less than 100 kilometers, 60 miles, in diameter, potentially numbering in the trillions, with an estimated total mass 100 times that of Earth. Despite their remoteness preventing direct observation, long-period comets, which take over 200 years, often somewhat longer, to complete their orbits around the Sun, are believed to originate from the Oort Cloud. Ernest J., the Estonian astronomer. In 1932, Öpik proposed the existence of a distant reservoir of comets, contending that due to the rapid depletion of comets during their transit through the inner solar system, a source of fresh comets must exist to continuously replace the comet supply. Although these comets have never traversed the inner solar system, they are challenging to differentiate from older long-period comets because of the gravitational perturbations of their orbits by the outer planets at the time of initial discovery. Through statistical reasoning, Oort demonstrated in 1950 that the solar system observes a consistent influx of several new comets, which had not previously traversed the system. This flux originates from the periphery of the Oort Cloud. He discerned it by examining the distribution of the initial values of the total energy of cometary orbits. These energies are proportional to A1, where A represents the semi-major axis of the comet's orbit. The original value of A denotes the comet's orbit while it was external to the solar system, in contrast to the osculating orbit, which describes the trajectory observed from Earth after being altered by the gravitational influences of the larger planets. Transits through the solar system generate a considerable dispersion of orbital energy in one. In 1950, Oort documented merely 19 precise original orbits of long-period comets. Given that 10 of the 19 orbits were clustered within a limited range of A1, it was concluded that the majority had not experienced this diffusion process due to the planets. The average value of A for these new comets indicated their origin distance, approximately 105 AU. This distance also induces perturbations due to the proximity of neighboring stars. Oort concluded from the coincidental distances that comets infiltrated the planetary system due to stellar disturbances. Subsequently, employing a somewhat larger dataset of recorded orbits, American astronomer Brian Marsden determined that the region of the Oort Cloud from which new comets emerge, the more remote section, lies between 40,000 and 50,000 AU from the Sun. At these distances, two mechanisms can perturb and redirect the trajectories of small icy bodies inward: the infrequent close approach of a star or a massive interstellar molecular cloud near the solar system, or the gravitational influences known as disk tides, imposed by the bulk of the galaxy's disk. The solar system's origin hypothesis predicts the presence and substantial mass of the inner region of the Oort Cloud, believed to begin at approximately 20,000 AU, despite not producing comets. The Oort Cloud most likely formed from ice planetesimals that first coalesced in the outer regions of the protoplanetary disk and then dispersed due to the gravitational influence of emerging giant planets. The extent of the Oort Cloud into space is uncertain. However, Marsden's findings indicate it is nearly devoid of material beyond 50,000 AU, around 1/5 the distance to the nearest star. The heliopause. The heliopause, a teardrop-shaped region surrounding the Sun, is between the Kuiper Belt and the Oort Cloud. It comprises solar magnetic fields and the outward-flowing solar wind, which consists of protons and electrons. The heliosheath, situated closer to the Sun than the heliopause, is a transitional area where the solar wind decelerates to subsonic speeds, which are slower than the propagation speed of disturbances in the interstellar medium. The heliopause tail is estimated to be 110 to 170 AU, 17 to 26 billion kilometers, 10 to 16 billion miles, away from the Sun. The Sun's trajectory across space induces interstellar gas fluctuations, affecting its structure. All principal planets, including Earth, situate their trajectories well within the heliopause. No satellite has yet attained the heliopause, although the Voyager 1 and 2 probes, launched in 1977, are the nearest at distances from the Sun of 105 and 85 AU, 16 and 13 billion kilometers, 10 and 8 billion miles, respectively. Voyager 1 and 2 entered the heliosheath in 2004 and 2007, respectively, at 94 and 84 AU distances from the Sun. We derive knowledge of heliopause from its influence on cosmic ray particles entering the solar system post-encounter, and from the radio emissions produced when solar material expelled during coronal mass ejections traverses it.